I forgot the intro screen, but there was a tech issue this morning. No! Can everyone hear me? Can everyone hear me? Can you guess what the tech issue is that I was dealing with for the last 20 minutes? You can hear me. I bet you can't guess the 50 points if you can guess the best tech issue, the tech issue we are having currently. I'm going to try something real quick. I'm going to try deleting the source. I know. Yeah, it's the... No, so what it is... Here, wait. Watch this. Let me do this. Let me go to Zoom. Let me start Zoom real quick. And my video is working. I think there was another tech issue too. So I think the two tech issues compounded on each other. And so I debated whether or not I would just do, let me lock this meeting. Don't think I was going to randomly join that quickly, but let me go to lock meeting. Lock meeting, you can lock meetings in Zoom. So here I am. Here's Brian, just so you don't think there's a random person. But I'm in my cave right here. So I think, I was having some issues with, does it say? Oh, it does say the meeting ID, but it's locked. Can't get in the meeting. There you go. Let me, I'm going to try one real quick thing. I'm going to try deleting the source. I'm just going to play with my hair like that too. So you guys can now see me. I do exist. I debated trying to you see, I can't put myself over here. But what I can do if I really wanted, so I could go to the main screen and I could put myself, can I change this window here? So I could put myself right here in the main screen. Oh, there you go. There's where, so I could put myself over here in the main screen. What does everyone think? I'm not mirror image, so if I look the wrong way now. I'm looking the wrong way. So continue without audio. What does everyone think? What's the solution to this? What I'm going to try real quick. Here, let's just do a real quick try. I'm going to try deleting leave meeting. So there we go. Let me try just deleting the source inside of here. Let me look at one thing. Go here. Okay, there we go. Delete that. Let me delete the black magic. The thing we use is called converting video. Stop converting. Stop converting. Yeah, what happened was I had another tech issue and I loaded up OBS. So I don't know if OBS is still running. Aw, thank you guys. I don't know if OBS is still running. If I delete that source, it's gonna... I've got all the filters and everything on the source. It's probably gonna be one of these things I have to deal with afterwards. Video capture device. I'm using Streamlabs OBS. And it's not showing any video on any of these. I think it feels like... Let me try new video. Let me see if I can... Just real quick. There it is. Really, what is going on? It's coming in as a different source. Can I edit the other source? All right, well, let's do this really quickly here. You ready? So everyone can see me on the screen now, I believe. And yeah, so that's weird. Okay, cool. Wow, what the heck? Let me go filter on this. So no filter applied. But 2 seconds. Sorry. Where's chroma key? Color correction scaling. Color key. Cool. Did they change what it was? Green. It's not green. Custom color. Oy. Is that... Well, okay. You know what we're going to do? I'm going to not worry about the chroma key right now. And I need to mirror image this. 2 seconds while I mirror image this so I'm not looking the wrong way. You know what we might just do? I think the easiest way. I might, one moment, plus video source, video capture device, add source. Why is it? It's registering it as a different source. I don't know why. And so now I bring this down to here. And I wish all my lights are on, so I don't know why the alpha would be so different. Filters, color key. Why is it not registering the color? Let's try one last thing here. We will be starting in 30 seconds. Similarity. There we go. Sorry. You have to, I spend a lot of time actually working on my color key and everything. Custom color. Don't I usually put it over there? So if you bring it up too high, you vanish. If anyone's ever done chroma keying and stuff, you vanish. So custom, really? Okay, well, I'm not gonna worry about chroma keying right now. See there, if you can see it start to go away right now. There we go. Okay. Okay, I think we got it. Oh no, I'm vanishing. Sorry. You're seeing the behind the scenes. So I need to bring the alpha down. What do you guys think I should do? Just leave it as is? It's going to take a lot longer than I want to take to do. I'm very sorry. For some reason the source got messed up. And I've got all the custom settings. I'm going to put this back down because it's going to look really weird if I do that. Okay. I know, right? So yeah. Sorry, I can make myself vanish away. Okay. Let's see right here. I'm over here. I'm going to make myself smaller for today. So I'm not blocking the screen. You can kind of still see there's still a little bit of alpha on there. So I'm down here. Sorry for the change in perspective. I'll figure out what was going on here. Very, very sorry. Let's get started. No more tech issues. Let's hop back in here to multiple regression. How's everyone doing this morning? How is everyone doing? Even my Red Bull's over on the side. Camera source got changed around. I don't know why. But how is everyone doing? There's your entertainment for the morning. Very, very sorry. 2 tech issues this summer, but it's what it is, just so people can know. With me moving to Texas, I'm constantly like moving things in the room and things get unplugged. And there's literally just wires strewn about across my bedroom right now. So I literally broadcast from my bedroom. Just like you can literally, the green screen that's right behind me right here. So it's, yeah, Crab Rave. Oh man, they can't take us down for a millisecond Crab Rave right there. You know, they can't. I'm going to figure out how long we can play the Crab Rave for. That's my goal in life, is to figure out how long you can play the Crab Rave. I need to go to privacy.com, not an advertisement for them, where you can make your own single-use cards. It sounds like totally an advertisement. And I need to make a card so we can get our Crab Rave back. So, and I don't think I have the delay on my voice either, because I've got maybe it's on my audio. I think I do. I have everything so finely tuned with all the settings where literally I've done all these tests where I've like synced. So I'm going to go back and look at that to see if that's synced later. What's up, Alex? Okay, here we go. Let's do this. Okay. So we have been talking about multiple regression yesterday. So we're talking about multiple regression. What is multiple regression? Can anyone just quickly, 100 points in the chat. Why not? We're going 500 points today on these Fridays. Sorry for all the tech troubles, but we're going 500 points. These are 500 points Fridays. So you can get up to 500 points, 100 points to start out. What is multiple regression? We need a really good description of what is multiple regression. What is multiple regression? Who knows what multiple regression is? Any ideas? Brennan right there really quick with greater than one variable. That's exactly right. It's more than one x variable. More than one x variable. That's all multiple regression is. It's just really quick. Boom, we know what it is. You got it right there. And now we see that when we look at our multiple regression equation, ooh, Alex, I like Alex's answer for 100 points right there. Estimating the relationship between a dependent variable and more than one. Because if it's one variable, that's simple linear regression. If it's one variable, that's simple linear. If it's more than one, it's multiple regression. So key right there that if it's one variable, it's simple linear. And if it's more than one, it's multiple. Key that we know this pretty instantaneously, the definition of multiple regression. And I can do a lot of trick questions on the test. And good job on the test. The test grades are going to have a little curve. I think the average right now is a 70. So it looks like a 5-point curve on the test. There was a typo on 2 questions out of like the 60, 70 questions I wrote. Some people got hit by 2 of them. Some people got hit by 1 of them. Some people got hit by none of them. The answers should be released this weekend, so you can look over them. Please tell me if you see any other typos. And thank you to the person who alerted me of them by saying they thought their test grade was a little bit lower. I went and I looked over every question. And I had planned to do that, but I needed people to take it before I look over it. And it's just the fatigue of writing questions, and then you click the wrong answer. So people who got, there was a little bit of luck in there because some people got a wrong answer that was right. So I didn't lower grades. I'm not going to lower a grade. I'll only give more of a grade. So I didn't want to pull down someone's grade because it's like, you thought you had a 25 out of 30, and now you got a 23 out of 30. So I don't like the idea of that. It said you had a 25. Well, then if you got that because of my mistake, you got it. So, but there will be a 5 point, not 5 point out of 30 curve, not 5 point out of 30 curve. There'll be a 1.66 point curve out of 30. Is that correct? Something close to that, like 1.5 points. So if you got like 24, you got 25.5. We'll be able to see our test. Yep, this weekend, I think, is when everything comes out, Connor. This weekend is when everything comes out. Please tell me if you have any questions about it. I already gave one person in 474 had a question about one of them, one of their questions, which was different. And I gave them points back because of the way they interpreted the question. They said, wouldn't it be this way if it was this? And I was like, I never expected anyone to interpret it that way. And I gave them points because of the way they interpreted it. And they made it was pretty obvious because they were like, Brian, you had said this, wouldn't it be this? And I was like, well, I meant this. And they're like, oh, and I was like, but since you interpreted it that way, I should have been more specific in what I said. So, I don't always get points back. I don't always make changes, but it was clear to me that when they read it a certain way. What it was is I should have said bivariate relationships, because I was like, oh no, I shouldn't. They thought I meant bivariate relationships, but I should have said univariate, because I was like, what can be used to analyze quantitative and categorical data? And they thought, and they showed me a slide where I was talking about quantitative categorical, and I meant like univariate relationships between quantitative and categorical. And what could you use to analyze what function? Here we go, 100 points right here. What function can you use inside of R to analyze univariate and quantitative data? And there's quite a few answers for this. So 100 points, first few people to answer. This was a 474 question because it deals with data validation. What functions can you do in R that would analyze univariate and univariate quantitative and univariate categorical data? What function can you deal with inside? What function can you use inside of R that would deal with univariate quantitative and univariate categorical? There's a really good one. And the really good one was the answer. But they thought I was saying, like, plot, boom, 100 points, Brad. Plot works. Plot's a smart function. Not hist, actually, though. I don't think hist will work. Good. Right there, James. You get 100. Nicole gets 100. Plot's an answer, too. Emily, what other functions are there? What other functions are there? ggplot, I'll take ggplot. ggplot as a package. Bar plot, not bar plot though, because bar plot is for categorical. Bar plot's for categorical, hist is for quantitative. But plot is a smart function. So if we go here and we make something like, my gosh, let's call this levels. And we're going to go here and just go, we need to go factor. Any other ones? Let's go M, F, M. No other ones? Because I think if I go hist, it might. We'll see if it does it. I'll be shocked. It doesn't like it. And because it doesn't, it wants it to be. Is there a function univariate? Nope. Good guesses there. How about summary? What? M and what? What is going on with the world today? What is going on? Factor with one level. Oh, I didn't concatenate it. Oh my gosh, okay, there we go. Now let's see if hist works on it. Hist shouldn't work as far as I know. Yep. It must be numeric. I didn't concatenate around it, so that caused an issue right there. But summary works. Any 500 points? Last person know or anyone know the last one you can do? What's another thing you could do? We could confirm this by making a numeric vector too. We could call this numeric. But box plots are only quantitative because box plots and histograms go together. This is good review. These are things, don't worry, this is practice. LM, Brennan, 100 points, you're right. LM will work on both, but not really univariate, but that's still a correct answer. Linear models, I know you're thinking it's linear. No, because it's linear. Yeah, GLM will work. GLM will work. So that's a secret. GLM will work, but not LM. That's where the confusion was, Brad. Brad, that's it. That's where they got confused. because box plots are quantitative, but bivariate box plots are quantitative categorical. And that's exactly where their confusion was. And then they even showed me where I was showing it, and they're like, I thought you had said this, and that's where their confusion was. And they made it clear because a singular box plot, like a box plot, which is what I was intending, is quantitative. Like this is quantitative. But multiple box plots, if you talk about like, multiple box plots here, that's across categories with a quantitative Y. And so that was the issue right there. Does that make sense? And class, yep. Oh, class would work. Yep. Class works on all of them. Great job, Alex. 100 points, Alex, right there. Side-by-side box plots. Yeah, and that's what if I'd written side-by-side box plots, that would be the answer. And so I could have been like, no, it doesn't say side-by-side box plots. I think I put box plots plural. So, and then you can, yeah. But the other answers possible are things like table. Table will work on all of them. So table works. Just gives you a table, and you can make a table of this if you want. Does it not want it? Ooh. Oh, numeric's not found because I didn't run it. So you can do all of these things right here. STR, structure. Why don't you run structure on a vector? Yeah, you get it. Shows the vector. I've never run structure on a vector, but I was pretty sure it would work. Usually I use structure on data frames. Glimpse. Yeah, I've never tried glimpse on that either. Let's try this last thing right here. Glimpse is in dplyr, and so glimpse might work. Glimpse is just gives a better version of structure. So really good practice here to know what the functions do and what they work on. Just make sure you kind of have this understanding in the background and start utilizing it. Streamlabs is doubling up. Brian's green screen's not working right. What's going on? So I know Streamlabs got a new profile pic, and it looks awesome. I like Streamlabs' new profile pic. So standard errors. What is the word? 100 points. This is Friday. Time to wake up. What is the word we say for standard error when we hear standard error? We need to hear like standard error of the confidence interval, or when we make predictions for the mean of y given some x, and that is our what? We say what? 100 points. What do we hear when we see standard error? Uncertainty. Sylvia right there, 100 points. Ryan right there, and Nicole, I'll take predicted, but it is uncertainty. Mila also, and Brennan. It is uncertainty. So this is your uncertainty when you make predictions for the mean of y given some x. This is your uncertainty when you make predictions for an individual. Standard errors are just uncertainty, and we want those uncertainties to be as small as possible because the uncertainties, another 100 points, are part of the what. The uncertainties become part of our what that we build. Our uncertainties become part of our what's that we build. Our uncertainties become part of our what's. Our model, but specifically what? It's on the screen. It's on the, I can't like point to the screen today. The uncertainties will be specifically part of the what. They'll be making the uncertainties, the confidence interval, Mila right there, the confidence interval, because we're saying, here's what I predict the mean of y to be given some x. Here's what I predict an individual to be. So you care about these uncertainties because what happens when you have more uncertainty, your confidence interval will get wider. So usually we go out 2 uncertainties because it's a 95% confidence interval. So when you talk about this right here, you want the smallest possible uncertainties. That's what you want. Now checking the assumptions. This will be day number 3 of checking assumptions. So I feel so good about this because you've got this. You know how to do it. Now, one thing I want to point out, great questions last night. I was answering, I'm trying to remember multiple people's questions about checking conditions. Please email me when you're stuck. I check my email, try to email back within, usually there's this buffer where I'm getting caught up from the start of the day. And then I get finally caught up around 3, 4. And then I start after like 5 or 6, I'm good to go because I teach morning classes. And then I eat some lunch, then I get caught up on emails, and then after like 5 or 6, I'm like caught up, so I'm pretty quick on emails after 5 or 6. Now, don't worry, email me at any time, but I just want you to know if you email me at like 9 a.m., and you're like, Brian, you said you email back quickly, and then it takes me till like 4 p.m. to email you. It's because I'm teaching, and then I'm answering emails. Anyways, I've had one person who said that one time. They said, when I joined an online class, they were like, I expected you to email back quickly, and you didn't. And it took me like 10 hours to get back to them, but I was like teaching all day. Anyways, I was like, okay, I'm sorry. Anyways, checking assumptions. When we check assumptions right here, what we need to do is we need to make sure we are very clear to the reader. And I really like the questions I was getting. Like the questions I was getting was, how bad is bad? How do I know if this is bad? Well, here's what I want you to do, and I think this will help because a few people were wanting that last night. It's a great question. When you look at this, I want you to give this one a rating A through F. Like this brings home a report card to you, and I want you to give it a rating A through F. Who's got a rating for this? 100 points. Who's got a rating? I want to see a rating for this A through F. I want to see a rating for this one A through F. Got B minus, A minus. I like that. There's 100 points right there. Now, I be careful though. I don't want to go below a B on this. I think a B, like this right here, the only issue is these points, but these are still in the decent zone. So I think the ratings we should give this one are B minus through A. It's not A plus. I wouldn't go A plus on it. I'd maybe do B minus through A minus. And there's going to be variation. But no one should give it an F, and no one should give it an A plus. Does that make sense? No one's giving this one an F, no one's giving this one an A plus, because it's not perfect. This one right over here, it's got a little bit of a problem here, a little bit of a problem here, but mostly stays in the line. For this second one, 100 points, all those answers. Keep giving the points. Let's give, because everyone as much as we can. This one, I don't know if I'd give it a D plus. That seems a little, no, it's a little, no, don't give this one an A plus. The second one an A, it's a B to me. Just give it your rating. A C's all right. This one, the problems with this one are that and that. But we're going to see worse ones. We will see way worse. Here, let's look at, do we not have a way worse one? That's no fun if we don't have a way worse one. We do have way worse ones, and I can make one pretty quickly. Let's just go in here, and we can make very bad QQ plots. So if we're looking to see if something follows the normality, we can just go here to Data, Survey 10. We don't have Reg class loaded up. Let's go here to Library, Reg class. And then let's go to Data, Survey 10. And let's look at a QQ plot for normality. And this is not from a regression, but it is a QQ plot for normality, which we should know how to analyze, see if it's normal. And if you look at this right here, what would you give this one? A through F, what would you give this one right here? It's got problems here. D minus, D, C, C minus. Yeah, this one, I like the D range for this one because it's got big problems here. It'd be really, yeah, if everyone's saying D minus, yeah, this is really, that one's, if we go here to, how about this one? This one, if there's only a few grades I would accept for this one right here, what grades would you give this one right here? If you saw this for the normality, what grade would you give this? Yeah, an F. Yeah, this is F plus. I'll take him for any cracking me up 100 points. Everyone's getting 100 points for these answers. So this one right here, remember, it should follow the red line in the middle. The better it follows the red line. F minus, minus, minus. Cracking me up, guys. So this one is really bad. And remember, this is not linearity for the model. It's normality of whatever we're checking out. So when we make a model, here, we'll make a really quick model right here. We can, and we'll make a multiple model. Why not? We're going to predict height from GPA plus weight. Does everyone see how to add more than one variable to a model? Does this make sense? How to add more than one variable to a model is you just do height, GPA, weight, and then you do data equals. Now here's a trick which can cause small issues sometimes. If you attach your data frame, then when you're typing something like height will appear. Now that can mask certain things, which means it can have things in the environment that are duplicates. Like if you have the same name of something, it'll overwrite it. It can cause small issues, so watch out. This is an iffy command. But now if I were to type weight right here, it's going to show up. See, there's weights there and there's weights. I don't want the other one. If I go plus and I go text per day, there's text per day right here. So the purple tag right there tells me it's another variable I can use. And so now it's got the autocomplete feature, and I've made my multiple model. And now we're going to do the check regression. I'm going here to check regression, and all you put in is your model M, and we run it, and here we are. Now let's take a look at this. You ready? So what do we have? We have right here the linearity. And the linearity looks good or bad? Linearity looks good or bad? Does that line go through the middle of the data? Hint, look right here. Wait, look over here, look over here, look over here. This line will always be like this, but you don't want to see where the points dip below in a certain way. Do you see this? This is the issue. This is all right. This is bad because this line is not going through the middle of it. Does that make sense right there? And we got an outlier right there. Who said outlier? Casey, 100 points right there. Yeah, there's outlier, which is also going to be showing up over here. That's the outlier you notice right there. So that outlier is extremely low, way lower than we would have expected. So right here, it looks like the linearity if you do this properly here, I've done this so long, I usually just go and look at the plots. So because yeah, I mean the p-values are going to be what the p-values are going to be. So, and here, why do I say that? The p-values you usually fail. If you do a lot of these and you've done a lot of regression and you've been doing them as many times as I have, usually you fail on the p-values, and then you look at the plots, and we're more likely to look at the plots and be like, yeah, that looks all right. So right here, you see that the p-value for the overall model fails. The p-value for the linearity of GPA fails. The p-value for the linearity of weight fails. We pass the p-value for the linearity of text per day. The p-value for equal spread fails. The p-value for the normality of residuals fails. So we need to look at everything but this. So we're going to have to bring up some more plots here in a moment. But when we investigate this, that's the only thing we don't have to investigate. This is the only, is that clear to everybody? When I talk someone through what's going on right here, as we practice this, as we need to know how to be thorough, the only thing I don't have to check off is looking at the linearity of the variable text per day. Everything else I have to look at and visually check. Like right here, this is the linearity of the overall model. And then over here, which I'm behind right now and I can't make myself, I can make myself finish if I really want. I can go here. Boop. And right here is the linearity for, right here, it's not that it never, right here is the normality of residuals. So text per day, well, now we can't fail it, Brennan. So good question. Since text per day has a p-value above 0.05, we've passed the text per day. And I put this on the final and people just, it's because we think high p-values are bad. They're like, oh, we failed that one because it's bad. All the other ones are passed. And it's like, I can just do a multiple choice here and I can say, which of these is correct? We pass all the tests, we fail all the tests, we pass all but text per day, we fail all but text per day. And then it'd be we fail everything but this one. Every test is failed but this one. Does that make sense to everybody right there? Like, hopefully with this week, we've really made it clear how these tests are done. Because feel free to ask, don't worry. It's that high p-values indicate that we do not reject the null, and the null is that there's not a problem. And I believe it's many equals true. We're going to look at the extra plots right here. And it should be extra equals true. Extra equals true. So we need to go here to the check regression, and we need to do extra equals true. Got to type out. So the extra equals true right here. We're going to get the extra plots. Let's take a look at them real quick. And here's the extra plots. I need to vanish once again. So the only one we don't need to look at, the only one we do not need to look at is text per day. And text per day is right here. And once again, don't need to look at it. It looks like, which of these looks like it has the problem? Weight or GPA? Which of these looks to have the linearity problem? Which of these looks, is it weight? Which actually has a lower p-value. Hint, hint, hint. I'm not really seeing it there. Weight has a lower p-value. I mean, oh, it does. Then, yeah, that's why this is happening. My brain is just, it's still turning on. Weight does have the lower p-value, and it does have this right here where we see this in the overall model. If you remember from the overall model, we saw the bend happening right here, and that's what the overall model's failing with. Probably that bend from weight. I don't see it. If you notice, this just barely fails, and I don't see an issue with this line. I mean, maybe here the points are a little bit below. I don't see an issue with this plot. I see an issue with this plot right here. So yeah, I'm not really seeing it. I don't know exactly what's going on right there, but yeah, overall, it looks like the big issue is coming from weight. And that's what I would say to the reader. I would say, like, I think the issue we are seeing is coming from weight. And I think that's what's impacting the overall model, because that relationship, does everyone see how this right here looks a lot like the residuals for this? It's because weight is a really good variable in explaining height, and it's kind of overtaking the relationship. So my total analysis of this section of the part is, one, we did not need to look at the linearity for text per day. We passed that one. The linearity of GPA looks to be fine by examining the plot. The linearity of weight shows a problem, especially at the higher values of weight. And this problem we see carries over into the overall model, where we also fail. I have concerns about the utilization of this model due to the linearity condition as seen in the plots. Does that make sense? That's my full answer that I would write out to somebody. So I have concerns. Are we going to use it? Maybe not. Maybe not. Because I'm a little bit concerned about the linearity. I'm like, I don't know. The equal spread looks to have issues where, look at the top part of the model. It looks like it's getting smaller equal spread. Do you see how it's thicker, smaller? So we look right here at this plot now for the equal spread, which is for the overall model. There's only one plot for equal spread. It's the overall model, and it's this one. And I'd say it's getting tighter right here, which we don't want to see it go from thicker to tighter, or thinner to tighter. Thinner to thicker. It doesn't matter. We want equal spread throughout the model. Last but not least, the normality of the residuals I need to vanish once again right here. When it goes to normality of residuals, I'd give this a C-. Overall, I think this model has problems, and I'd be very hesitant to use it. So did I say not to, and listen to my words right there. Did I say do not use this model? I didn't say don't use this model. I said overall this model has problems, and I'd be hesitant to use it. So I might be like, let's use it. So I'm trying to not be like, use it, don't use it. I mean, there's models you won't use. Like, there's models you'll be like, no, don't use that model. But overall, I'm saying, I don't know if I'd use that model. I mean, it's a little bit worse than I'd like. You could use it, but I'm like, I don't think it's good. Does that make more sense, how to like talk through these plots and to say if the plots are good or bad? Does that make sense? I'm gonna ask a big question right here. Which of these plots right here is an amazing residual plot? Plot 1, 2, or 3, 100 points. Which of these plots right here is like an amazing residual plot? Which of these plots are you like, whoa, that is so amazing? Which of these plots right here would you be 3? 3 is beautiful. 3 is amazing. Because what should a residual plot look like? Nothing at all. It should just look like random points. And this right here is a perfect residual plot, near perfect. I mean, you'll be like, what about this point? Well, I mean, that's kind of just your point that's a little further away, because you're going to see points scatter out. You're going to see 68, 95, 99.7. So that is an amazing residual plot right there. It looks just like we'd want to see. Those are the kind of residual plots we want. And those are all pretty good right there. Linearity condition. Once again, when we look at our residual plot right here, we have to make our own imaginary line. So this is where I think people get stuck, is because when we get the R output, it puts this line right here, which is the black line. So this black line you're getting right there, this black line right there is this black line right here, and you have to imagine this line. You have to look at your points and say, okay, my model goes through the center. It's got kind of a, did you see this kind of, it goes up and then goes, uh-oh, that's bad. So that model right there looks like this black line is not going through the middle of the points. You can see some over here where we do have it going through the middle, but we have unequal spread. So this one does not look to have an issue with linearity, even though we're saying, oh, it might bend a little bit, but that's not that big of a deal. We want to see no patterns, exactly. And this one has a pattern right here. This one has a pattern with changing spread, and also we see a bend throughout the model. So we don't want the model to bend. We don't want it to change spreads. We want it to look nice and perfect like this right here. This is like perfect. These are not bad. Like, these are okay. Like, that's okay. That's okay. That's really awesome. So, you know, once again, it's like this one gets a B, this one gets a B, this one gets an A+ and a gold star. They did awesome. They did amazing on that one. So don't try to think of it as like perfect, like it has to be perfect. Like, these right here are all, this is an A+, this is an A+, this is an A, it's an A-. I don't like that it has these gaps, but I can't say it's bad because I don't have evidence. So you might say, but wait, aren't these patterns bad? you're just missing data points inside of here. You don't have values of X right here to make predictions, so you don't really know what your model does. This happens in data, and it's just weird residual plots you can get, but everything looks to be consistent. It's going through the mean right here at all points, like the line goes through the center of the data. It has consistent spread, and we look to have a 68, 95, 99.7 GSCO. It's a lot of points in there, more points here, and then 99.7. We'd want to draw our QQ plots for normality to look at that, which where do we have these? But I don't have it for those currently on the slide. So once again, now here's a big thing you should know where I trick people on the test. How many conditions do we check for multiple regression? I guess there's a few ways of phrasing it. How many conditions are we always checking for regressions? How many conditions are there to check for regressions? How many conditions are there to check for regression? There are 3. There's the linearity of the model, or the linearity of parts of the model. More on that in a moment. There's the equal spread, and there's the normality, which you should know the plots to look at for all of these. But the linearity is now broken down into multiple parts. The linearity, when you look at linearity, we will now look at the linearity for each of the x's, and we'll also look at the linearity for the overall model. So your overall model is the plot that we've been looking at all along. Just remember, your overall model is this right here. This is the overall model, the one we've been looking at consistently. But now you need to look at the linearity for each of the x's. So you need to go and look at the linearity for each x. You remember how my model had 3 x's, GPA, weight, and text per day, right behind me right here. So you have 3 x's, and you have to look at, if your model has 3 x's, the linearity for each of the x's. It's still linearity, but it's for each of the x's. 100 points, Nicole, right there. Yes, 100 points, Brad, for thanking also. That's why I like everyone helping out. It's really good when you put in the chat what I'm saying so you can read it, you can practice it. If you type it out, you learn it better. Just keep practicing and knowing what we're doing. That's the biggest thing. Why do we do this? Oof, I don't do, oh, we had the p-values on the screen a second ago. How do we do on all these tests? This is what usually happens. This is why I usually just look at the plots. But once again, please follow the steps. The sample size is large enough. Step 1 is look at the p-values. Step 2 is look at the sample size, and step 3 is look at the plots. How do we do on all the tests? Bad. James, 100 points are there. We fail at every single test. We failed every one of them, and that usually things like that happen. I'm going to zoom in on this part right here. What is the only condition you think I would give it? One of these conditions I'm giving it a B on. One of the conditions on the screen right now I'm going to give it a B on. I'm talking about these up here. One of these conditions I'm going to give it a B on. What condition will Brian give this a B on? Is it the linearity? Is it the equal spread? Or is it the normality of residuals? Which one is Brian giving it a B on? Normality, yep, Sylvia, you're right. The normality, it's got that, and it's got that, and it's fine. Yeah. So the normalities, I'm thinking it's fine on. Which is Brian going to give it like a super F on? Which one is Brian going to give it a really bad F on? First person, 100 points, who knows? Which one is Brian just going to completely fail it and say, no way? Linearity, Brad, you're right. The linearity, it bends. That's horrid. That's ridiculous. I'm going to give it like a D- on equal spread. I don't know. Maybe I'll give it an F, like a regular old F, not a super F. But equal spread is if you look at the X variables right here, which X variable looks to have the worst problems with linearity? I see 2 that I really... Tell me 2 X variables you think has a big problem with linearity right here. 2 X variables you think have a big problem with linearity. Give me both of them right there. Brandon, 100 points. Give both of them in one comment. Give both in one comment. See if you can see the 2. Give both. Yeah, sailed it and you're made. Yeah, I see it right here because there's this bend over here and there's this bend here. I mean, that's got a little there, so it's not great, but it's only 2 points. If you erase these 2 points, that's what we always try to remember. Like, if you can erase 2 points and you wouldn't see the issue, then, yeah, is it really an issue? This right here does seem to have a bend at the end. Is that a bend in the middle of the model? I don't know, because remember, it should go through the middle, but I see it more right here, and this is the main culprit. Like, this is number 1. What's number 2? Maybe this. Yeah, maybe this. I think it's most likely this. This is number 1, though. That's the Does it make sense how to read these plots? And we're actually checking the linearity for each x in the model. Who thinks they understand this? Is like, Brian, I got this. I know how to do this. I can check my conditions. I can look at the conditions and be like, okay, we're looking at the linearity, the equal spread, the normality, the residuals, and I know what plots to look at, and I know what the p-values mean. Can we get some yeses in the chat right here? Power me up with all those. I got this. I know how to check my conditions. I got this. Brennan, you're awesome. I like it. Sylvia right there. Remember to be thorough with your words on your assignments. When you check conditions, we're not just going to be like, it's good, it's bad. We want to say what's going on right here. So if you know how to check those conditions, you are good, because that's the last slide on it. And let's go here to descriptive analytics. Now, what's really awesome, and once again, I'm going to look to see if everything's graded the way I want, because I want to make sure it is. Really important to me. You got this, Corbin. You got 100 points, Corbin, and everyone else got 100 answering right now. So what we've done previously, I want to zoom in on this again, is we've talked about our interpretation right here for simple linear regression. And you get cheat sheets on the test. These are the types of things you want on your cheat sheet. And I miss our written tests because I don't want to be mean to people, but if you don't interpret things like this correctly, I'll take off points. Now, I can't do written tests because it's multiple choice and stuff like that. So, breathe a sigh of relief. Breathe a sigh of relief. But let's hop over here and look at this. What you should know right now is it's two individuals who differ by 1 unit of x are expected to differ by blank units of y, where the individual who has the higher y is expected to have the higher x, or if it's positive, the individual who has the higher y is expected to have the lower x if it's negative. So what does this mean? Let's explain why right here this is said this way. Everyone's like, why do we say it in such a weird way? Well, let's talk about it again, just to make sure we understand why we do the very thorough explanation. If you did the 201 explanation for this, if you went back to 201, and I need to change 201, but we have to change the books, and we can't change the books, you would say something like, for each additional pound you gain, which I really need, this will be all over the final. Oh man, this is like going to be multiple questions on the final. So I'm trying to, Alex, thank you so much, Alex, for all your questions. I'm so excited about writing the final because Alex is dropping so many questions and potential questions. And if you want to help out, go over to the Discord. Shout out to the Discord right now. Go over to the Discord, start looking at those potential questions, know how to answer them, because I'm definitely going to be leveraging a lot of those potential questions. So here's a wrong answer. For each additional pound of weight you gain, we expect you to be 0.07 inches taller. Did everyone hear that? If you want to be taller, what should you do? If you want to be taller, what does that suggest? For each additional pound you gain, we expect you to be 0.07 inches taller. This is the wrong interpretation. Gain weight. There we go. Like, I want to be taller. I'm just going to gain some weight. I'm going to go eat some cheeseburgers. If you like cheeseburgers, I like cheeseburgers. So that's my goal. My goal this weekend for Father's Day is to go home, make cheeseburgers for my dad. So like we can make them together. We're like, hey, Dad, let's just get some cheeseburgers. Let's grill some cheeseburgers, some cheddar cheeseburgers. Grill those buns. Like, man, I'm just excited. Good cheeseburgers and fries. Cheeseburgers and fries, homemade. That's what I'm just excited about, guys. Say, give, show your fathers some love. Say Happy Father's Day. Give them a call. Go see them. Whatever. Anyways, with that in mind, I'm going to say, Dad, you know what we're doing? We're not eating cheeseburgers, Dad. We're getting taller. We're not eating cheeseburgers this weekend, Dad. Our goal this weekend is to get taller. We're going to have like 5 cheeseburgers because for each additional pound we gain, our height will increase by 0.07. That is one of the worst interpretations we could possibly give. Let me say the horrible interpretation again. For each additional pound we gain, our height will increase by 0.07 inches. That makes it sound like a law that when you gain weight, your height does increase. We've all gotten taller via quarantine. Quarantine has made us all taller, if you get what we're saying right here. But what does this actually mean? What does this coefficient actually mean? 1,000 points, first person who accurately interprets the coefficient. I mean it. You're at 1,000 for the day. Who can accurately interpret that coefficient? Who can accurately interpret it? You need to know this. Go back to the slide, and I'll drop the coefficient in the chat, and you should know its height and weight. So in case I leave the slide, it's all you need is the coefficient now because we're predicting height from weight. And then you go right here and you can see how to interpret it. but you have to put in what it means. You have to put in what it means. And it'll be easier with multiple choice. It'll be way easier but then I'll switch numbers. I might even give you 6 possible answers because usually I have you write this. So I might put 6 answers on here. Between 2 people who differ by 1 pound, we expect their heights to differ by 0.07. Yep, pretty much it. And so Mila right there, I'm giving Mila 1,000 points too. So it's 2 people who differ by 1 pound are expected to differ in their heights by 0.07 inches. Now, Mila, we would add on the very end of it, the person who is taller is expected to have the greater, the person who weighs more is expected to be taller. Yep. There we go right there. Mila, amazing job right there typing out that answer. 2 people, or between 2 people, you can say. So there's flexibility if I do have people write it out. Like I wouldn't say, you didn't say 2 people, you said between 2. No, fine. 2 people who differ by 1 pound are expected, and the expected is key right there because we don't say they will differ. We say we are expecting them to differ because it's a model making predictions. 2 people who differ by 1 pound are expected to differ in their heights by 0.07 inches, where the person who weighs more is expected to be taller. Does that make sense? It makes perfect sense. That's exactly what we're talking about right here. Now we get into a really interesting scenario, and I really love, and these slides go through it. I might just show the slides because when you interpret this in a multiple regression, I'll go back to show you what it says. When you do this in a multiple regression, if we're predicting something like salary right here, we have here 2 variables. We have here education and experience, and let's show the models. Here's experience. And there's other variables, and here's attendance. It's just showing different univariate models. And what we get right here is a multiple regression model. And I'll go back and show the key slides that'll help you understand what's going on here. We have here a coefficient of education. We have here a coefficient of experience. But when we change, and this is, I'll show the key slide on it. When we change somebody's education, what is happening to their experience in months? Like when we say 2 people who differ in their education by 1 year of education, what are we doing in that moment to their experience and their months? Kind of a trick question right here. When I say 2 people who differ by their education in 1 year, what am I doing to their experience in months? What am I doing? So 2 people who differ in their education by 1 year. What have I done to their experience in months? I'll explain that in one moment, Ben. PCH is, which one is which? PCH is point style, and CEX is character expansion. That's what it means for. So CEX changes the size of the points. So it changes how big the points are. And PCH is a number 1 through 20, which chooses a point style. And I don't know what the acronym stands for, but it's just the style of the point. So when you do PCH, if you pick something like 1, 2, 3, 4, 5, it'll change it from like a triangle to like a circle to it'll do a different type of thing. And then CEX will change how big the object is. It's called character expansion. And Brad is totally right. When we say 2 people differ by education by 1 year, it'll do nothing to their experience in months. And the math is shown to you right here. When we have 2 people who differ by 1 unit of experience, if you have 2 people who differ by 1 unit of experience, mathematically, you'd expect these 2 people to differ by how much? Yep. Great job, Megan. 100 points right there, and Brad. So if you have 2 people, and Ben for asking the question right there, 2 people who differ by experience by 1 month of experience, because I think it's months of experience, or sure, whatever, months or years, we would expect them to differ by how much in their salary, in their monthly salary. 2 people who differ by experience by 1 unit are expected to differ by monthly salary by, here's the 2 people and their difference, by 12. And this is them differing by 1 unit. This person has 1 more unit than the other person, and we expect their difference to be 12. That's the mathematics, 2 people. But what did we say is going on with these 2 people's education? What are we assuming about these 2 people's education values and months at the job value? What about these 2 people's education values and months at the job values? What about those? That's E, that's E, that's M. What are we assuming about these 2 people's educations and months? Everything is equal. And that's all you have to change. That's it. Two individuals who are otherwise identical. That's it. You're saying they're otherwise identical, but they differ in whatever you're saying by 1 unit. So do you see how we practice the simple? Because then when we go to the multiple, here's the coefficient of weight. Two individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the person who weighs more is taller. Watch this. Two people who differ in, well, I could say it first. Two people who are otherwise identical but differ in their weight by 1 pound. Does everyone notice the only thing I have to change when I do a multiple regression? Two people who are otherwise identical but differ in their weight by 1 pound. Who thinks they get this right here? I want to see some more yeses in the chat. That's what gives me the power when I see yeses. That the only thing you have to change going from simple to multiple is acknowledging that they're otherwise identical in every single aspect. And all you're changing is this one. You're saying two things that are otherwise identical but differ in this one. 100 points right there, Sylvia and Dennis, who are otherwise identical. That's it. Two individuals who are otherwise identical but differ in this by 1. When do we use this? This must be used in multiple regression. Don't use this in simple. It's not bad if you use it, but there's no, it doesn't make sense. Wait a minute, you're saying they're otherwise identical, but you only have one characteristic you're looking at, so you're only changing that one. Two people who are otherwise identical but differ in this by 1 unit. Yep, that's it. James, 100 points. James, why not 300 points right there? Probably going to put you on track of that 500 really quickly. Must be used in multiple. Megan, 300 points. Another great note in the chat right there. These are the things we should have in our notebook, that this is the interpretation for multiple. In multiple regression, we must acknowledge that they're otherwise identical on the other characteristics of X. Key stuff right there that we need to know instantaneously. The intercept right here, meh. The intercept is when all the x's are equal to 0. So we rarely ever consider it. That's why I'm always like, intercept, who cares about it? Sorry, intercept, no one cares about you. This is someone who has no education, no experience, and no months on the job, which I guess that might exist. It's like, what are we calling education? Like years after high school? Or does high school get counted? Because what if someone says, I didn't finish high school, which is, I mean, it's fine. I mean, I think people should get their GED. That's personal opinion. Like if they don't, I have friends, family who did that. But, you know, like, how are we collecting this data? That's what I care about when it comes to it. Like, what does it mean to have zero education? I mean, does it mean you never even went to elementary school? So for each additional observation, you include that new variable. Wait, sorry, let me slow down. So for each additional observation, would you include that individual's new data to the regression, which would update the coefficients? Do we use the data in a dynamic way? Oh yeah, so well, yeah, you could, Brad. And that's kind of what, if you look at like they're, you know, to bring up, well, they're making current regression models with current world event with you know, like new cases and stuff, and they're just constantly adding new data to figure out the coefficients of whether the model's going up or down. And, you know, do we have good evidence of this? Do we not? Like, is it staying the same? Is it going up? Is it going down? Is the coefficient negative? Is it positive? And you make confidence intervals for the coefficient. That current world problem is a time series problem. I'm talking about the C19. So that's a time series problem, though, because then you have like lag coefficients and stuff like that, which we do have time series in the back of the book. But time series is a whole course unto itself, because time series data has a special way to analyze it to acknowledge the time series pattern in it, because it's like one thing that people don't realize, and I think a lot of people maybe know this now, when you compare numbers for C19, you need to do this week's numbers versus last week's numbers, or you could do this month's like average versus last month's average. Of course, monthly data is only going back like 3 months, so we have very few, you know, very small observations, so you're going to limit your power in that sort of analysis. Would lag coefficients be determined by squaring? Lag coefficients are just going back, so you can look at the lag coefficient by taking what was the amount 7 days ago. So a lag is like, let me lag this by 7 days and let me use it to predict. So you can use the amount it was at 7 days ago to predict what it's currently at, and then we can do an autoregressive model. So there's ARIMA models, autoregressive, iterative, moving average, and so I should do an ARIMA model on it just to see what I'm getting for predictions. But I think if the data sets, I mean, everyone displays the data, and then no one has the data in like a data set that I can just download and run an ARIMA model on. Which, let me just say this: with R, it's so easy to do time series because there's a library which I don't know if I have on this computer yet. Forecast, which it looks like got Forecast, great. Forecast has a thing called Auto ARIMA. And there's Auto ARIMA, and you literally just put in your time series data into Auto ARIMA, and it'll do a time series model for you and figure out the autoregressive iterative moving average. So R makes things so much easier. Like when I had to originally learn them, it was a lot tougher because you had to go in and change the variables around. So amazing things, lots more to learn if you can't tell, and it's actually all built on the basics. So and is often incorrectly even by professionals. And Dr. Petrie wrote this, and he means this, that a lot of people who interpret coefficients are doing it improperly. And I want to show you the perfect example of this. The perfect example of where people are misinterpreting coefficients is right here. Because what happens to your body fat as you gain weight according to this model? What happens to your body fat as you gain weight according to this model? What would this model actually do to the predicted body fat as you gain weight? Your body fat would go what? Your body fat would do what as you gain weight right here? As you gain weight, your body fat would be predicted. Now, I know it's not statistically significant, but it's not statistically significant. Like, well, it's still in the model. The coefficient is still in the model. Alex 100.8 would go down. It'd be predicted to go down. How does that make sense that, you know, when you think about it, let's think about it in the simple world. Two people who differ in their weight by 1 pound, the person who weighs more is expected to have less body fat. Now, with this right here, let's take a look at it. We're going to do it as a simple model first. So the simple model is only going to be two people who differ in their weight by 1 pound. So we'll go here to weight. I think it was lowercase. And you see now we're going to have issue maybe. Okay, good, it worked. Okay, good. Now, in the simple world, look at it in the simple world. It has a positive coefficient. Two people who differ in their weight by 1 pound, the person who weighs more is expected to have more body fat. Or two people who differ in their weight by 1 pound are expected to differ in their body fat by 0.16%. And be careful, this is a percent because it's body fat. That's the only reason. Body fat's in percentage. With a person who has more, the person who weighs more is expected to have a greater percentage of body fat. But why in the world, in the multiple world, why in the great wide multiple world, that didn't work, is the coefficient here negative? And let me tell you why. Because these two people are what? In the multiple world, these two people are what? In the multiple world, these two people are what? 100 points. What's the big thing Sylvia put in the chat a moment ago? These two people are what? The two people who differ by their weight by 1 pound are what? But close, Brad. I'm giving you 100 points right there. You're basically saying it. Otherwise identical. They differ. Everything else about them is identical. Does that make sense? They're otherwise the same. Yes, 100 points. All these people saying they're otherwise equal. That's what you have to know about the multiple world. What we're stressing so much about this interpretation. And so what does that mean? That means if right now we have a Brian, we would also have a Brian who is the same age, who is the same height, who has the same neck measurement, same chest measurement, same abdomen measurement, hip, thigh, knee, ankle, bicep, forearm, wrist. They're going to have all the same measurements as me. They're going to have every measurement identical to me. But let's say they weigh 30 pounds more. Everything is identical to Brian, but this person weighs 30 pounds more. What's the only way that this person could weigh 30 pounds more than Brian, but have every single measurement the same as Brian? What is the only way? 500 points first person. You get maxed for the day. What's the only way you could be, like, logically, just think logically, which we don't always have to think about these so logically. But what's the only way to have every measurement the same, like to have the same chest, same abdomen, same hips, same everything as Brian, but weigh 30 pounds more than Brian? And I know it's only a 1 unit change, but let's say they weigh 30 pounds more. They differ by 30 pounds more than Brian. So their body fat would be predicted. They weigh 30 more pounds than me. but we would predict that their body fat, and this is going to be a negative difference, would be 2.4% lower than me. They weigh 30 pounds more than me, but we're saying they weigh they have 2.4% less body fat. It's muscle. Sylvia and Emily are both maxed. Yeah, it's muscle. Because the only way to pretty much keep all the measurements, because they're going to be the same size as me, but weigh more, muscle is more dense than fat. Does that make sense to everybody? Great job, Sylvia and Emily right there. Muscle is more dense than fat. So because of this, this model is saying two people who are otherwise identical but differ in their weight by 1 pound, the person who weighs more is expected to have 0.08 less percent body fat than the other person. And I did right here that if someone weighs 30 pounds more, we would expect them to have, if they're otherwise identical and they weigh 30 pounds more, we'd expect them to have 2.4% less body fat, which is interesting because if you think about it, if you're trying to work out and get stronger and you're like, well, you may be like, I've gained weight, but everything, still fits. I still have all the same measurements. Well, it's like maybe you've decreased your body fat by this amount because the weight you're gaining, your measurements aren't changing. You're actually putting on muscle. You're more dense. Is it logical now why we're saying two people who are otherwise identical? It's not the simple world where it's like, oh, if you gain weight, we'd expect your body fat. And look, you know what's weird? Here, the coefficient is statistically significant. This is statistically significant. But in the multiple world, guess what? It's not statistically significant. That p-value right there is not. And we're about to see that craziness in just a moment. So in the multiple world, we have to stress two things that are otherwise identical but differ in something like fat by 1 unit. They're expected to differ by this. Here's their abdomen. So two people who are otherwise identical but differ in their abdomen measurement by 1 centimeter are expected to differ in their body fat by 0.89%. Please, please, please realize it's only this because that's the units of y. Whenever you interpret this, you interpret it in the units of y. We were doing like how tall someone is, but don't always do percent. It's only percent because body fat is percent. So whatever the units of this is, we do it in the units of this because that's what this is going to predict right here. It's going to predict this mathematically. Just look at it as an equation that's just trying to predict someone's body fat. So all these numbers over here are in units of this right here. Hopefully that makes sense. That's just trying to predict body fat. We might see a few more examples here. There's body fat using the coefficient of weight. Cool, cool, cool. And right here, isolating. This is the big thing. So this is what I like to point out. And people online don't get it because they don't like stats. When you add in a variable into the model, it's controlling for the variation in the other variables. So when we add something into the model, someone might say, well, maybe people's body fat is due to their age. Well, you'd say we've accounted for the variation in age. Well, maybe it's due to their abdomen. Well, we've accounted for the variation in abdomen. Anything that's added into the model is now controlled for. We've isolated the variation, and it's why we're saying they're otherwise identical, because if it is their abdomen, if it is their height, if it is their age, we have those variables in the model, and those variables will account for the variation if they are truly the ones in control of it. So how do we account for lurking variables in a multiple regression? All you do is just dump it in. How do we know we've included all important sources of variation? That's my problem when someone's like, well, how do you know it's not this? And I'll be like, well, what would you assume the coefficient is of something outside the model? If something's not in our model, what do you assume the coefficient of it is? I'm not saying you know it is this, but what is the null hypothesis for the coefficient of something outside the model? Without any knowledge, what would you hypothesize? 100 points right here. What would you hypothesize the coefficient of something outside the model to be? It's not in your model, so you have no knowledge of it. It's just they say random variable this. You say, well, without any knowledge, I have to assume the coefficient is this till evidence otherwise. What would be a good starting off point? Would you assume it's like, oh, the coefficient is probably 100? Maybe it's negative 100. Maybe it's 5. Maybe it's 20. What would you start off with as an assumption for a coefficient? Like the weight of something in the model. When I say coefficient, I'm talking about these things right here. What is the starting off point assumption for any coefficient in the model? This is a good test question. I'd probably put answers like 0, 0.05, 1, and 100. What would be the starting off point for any coefficient in the model? What is the assumption? There's silence. Sometimes I feel like I've gone offline. 0, Philip, 100 points right there. 0, 0. 0 is what we assume the coefficient would be without any other knowledge. We assume it is 0 because without any other knowledge, why would it be something other than 0? I don't know. I mean, I'm assuming it is 0 until evidence otherwise. That is what we assume. The standard error, once again, is the uncertainty, and we use this for confidence intervals right here, and this is going to lead to a new topic. Once again, we see how we make our confidence intervals. We just do the estimate plus or minus that amount of uncertainty, and this is the easiest code to do. If you have a multiple regression model, here's every variable. Please take a note on this. Jonathan, extra 100 points. Thank you for taking that note in the chat. We've got right here y tilde dot. This is every variable in the model. Let's do a summary. Here's all your variables. Someone gets 1,000 points. Please construct a 95% confidence interval for... I'm trying to find the easiest one. Give me a second. I want to find an easy one. They're all... I wish... yeah, let's do this one. Ankle. The top. Construct a 95% confidence interval for ankle. Construct a 95% confidence interval for ankle. Go. This is a test question now. Would there be a way to include everything but one variable without... Yes, Sylvia. Yes. You would just go here and do the following. That'll do it right there. Great. Sylvia, 1,000 points. Thank you for asking that. Yep. That's how you do everything but one variable. You just do everything and then you subtract off a variable. Amazing question, Sylvia. Really good question. Yep. And then when you see it, you're like, oh, that makes sense. You just subtract off the variable. Hopefully you see and you're like, oh. But I mean, how would you know that unless I told you? No, that's really, really good question. Hence the big points right there. Thank you for asking that. Who else is going to get maxed on points for the confidence interval for ankle? Who else is going to get maxed on points for the confidence interval for ankle? Take your time right now. Pause the video if you're watching this. See if you can solve it, because I love these types of test questions. They're very easy to write. If you know it, you know it. If you don't, you don't. That's a good test question right there. If someone has no idea how to do this, they're like, what is this? What do I do with this output? 95% confidence interval for ankle. So the test question would probably read, without using software, compute a 95% confidence interval for ankle. This is possible knowing how a 95% confidence interval is computed. And then maybe I'll put a note. Assume the sample size is large for this problem, because that if the sample size is very small, then that would cause the t statistic to be really odd. But we let the software do it. But you should know this about 95% confidence interval. Has anyone got any idea? So we got a good pause right here, but who knows what's going on? How do we compute that 95% confidence interval? Let me scroll up a little bit so you can see. I know which numbers are the ones you should be using, but maybe you don't. So let's go right here. That should show you which numbers you should be using. What numbers do you need to be using for this? Let's look at the equation again. I see an estimate. So you have an estimate right here, and you have a standard error. There we go. There's the estimate, and here's the standard error, and there's the tip. That's what we need to know. So, who's got ideas? Who's got ideas? Who knows? I'm trying to compute it in my head. I have to do 41, 16. Okay. Why can't... Okay, I'll type it out in the chat. I'm doing 2,000 points for this one. Let's see. Who's got... Alex, good guess. 100 points, Alex. Good guess. Remember, a confidence interval needs a lower and an upper. Confidence interval needs two sides to it. So I'm going to put the answer here in the chat. Let's see if anyone gets it. When you hear 95% confidence interval, what do you think? What do you think? Go plus or minus. Who's got me on this? Who's got me? Sorry, I'm thinking of the answer while I do this. Okay, so I'm not using the calculator, so sorry if I make an error on this. Okay, I got it. There we go, Mila. Great job, Mila. Plus or minus 2 standard errors. You got it. That's it. So you notice the 2 standard errors. So what's it going to be? What's it going to be? Mila, you get 2,000. Let's see who else. Who else is going to get this? Who else can solve it? That's the answer. Yes. Henry, you're right. That's what I had right here. And I put the lower bound as the lower. Henry, great job. Let's see. And you could, if you know the code, you could go right here and you could take the code and go confident. And on confident, you could go to M and you could see the ankle one right here. Now, if you notice, there we go today. Yes, James. Here, James, you get the points too. And if you notice, we're all super close to this. So everyone's giving within just fractions of percentages within what the answers are. 0.57 is the right for the upper, and then we're just a hundredth off for the bottom one. So we are estimating it by doing plus or minus 2 for a 95% confidence interval. We are 95% confidence interval that given two others for. Ooh, I kind of like that, Brad, right there. Brad, I'm giving you 2,000 points. Yes. And if you notice what Brad is saying, ankle could have a what? Could have a positive or negative. So the way I would change your interpretation just a tiny bit, Brad, is I am 95% confident the true coefficient, which is what we would expect the difference to be. So you kind of elaborated. Your answer is decent. I mean, it works because you're saying the coefficient is how much we expect two otherwise identical people to differ by, given they differ by 1 unit of ankle measurement. But I would just say I'm 95% confident the true coefficient of ankle is contained in the interval negative 0.24 to 0.56. Does that make sense? I am 95% confident the true coefficient for ankle is contained in the interval negative 0.24 to 0.567. And look at this. The interval definitely contains what? The interval definitely contains what value in the middle of it? Closer to this value. Well, yep, closer to that value. In the middle of this interval somewhere is what value between it. As it goes from negative to positive, the interval contains what? 0. And since it contains 0, that means right here that the p-value is above 0.05, not significant, which is the null hypothesis because we assume. Now look at this one. This is the most significant, and look at it. We can estimate its interval because that's a standard error of about, like if that's 88%, that's 8%, I guess. Oh, let's use that. So 8 minus this, that's 72, plus this, that's 104. So that was abdomen. I say 72 and 104 for abdomen. There you go. 72 and 104. We did that in our head like this. Does everyone see the trick I'm doing to find out the numbers 72 and 104? Did everyone catch what Brian did just a moment ago to figure out 72 and 104 by looking at these numbers here? I called this 88. I went 96, 104. I called this 88. I went 80, 72. I'm just taking and subtracting or adding 2 standard errors to this number right here. Who thinks they get that? Like, does that make sense? Hopefully it does. I know I'm asking that a lot today, but I know it's a Friday too. It's one of those big days. Look at one of the least significant intervals. Look at this interval right here for knee? This interval for knee basically starts at what? It's so close to what? The interval for knee has a lot of uncertainty relative to it, and it starts right at what value? It's right next to what value for this one? It's so close to what? And look at how insignificant it is. It's so close to 0. Yeah, because you're saying knee is, and we have so much uncertainty in that estimate. Relative to the estimate, it's going to make an interval for knee right around 0. So when you look at knee, the interval for knee is like centered around 0, and it's like negative and positive, and right 0 is like in the middle of it. So you're like, yeah, knee, I don't know what knee does. I mean, what does your knee do to your body fat? I don't know. I can't tell you. That really doesn't do much. Abdomen, do you think abdomen is related to your body fat? Do you think abdomen is something that is significant in predicting people's body fat? Would you say abdomen is? Yeah, I'd say abdomen is. Abdomen's like the most significant thing. Abdomen is the most significant, following closely by your wrist. If you look at where they take like those calipers, they'll do it like in these areas. If I know it correctly, in your forearms, so they'll do around your arms, all those things. And then we've got some neck right there. But if you look at what stands out, it's your forearm, it's your wrist, it's your abdomen definitely, it's your neck, and then maybe things like your age. But age is not significant. So more on how we'd actually make a model that would be the best. Hey, there's my mixer. So there's how we make our confidence interval. But we see something, well, 95% of 95% confidence intervals are constrained truth 95% of the time. And we're going to do VIFs today. And I think that's where we'll end. I think we can do VIFs. Oh, we got to do that. So in the standard error, yeah, sure. Standard error is uncertainty. Don't worry. Okay. R squared sub I. R squared sub I is the R squared for the ith variable in the model. And what this means right here, when we look at R squared sub I, we're talking about how the x variable in the model is explained by the other variables in the model. So please take a note, r squared sub I, you'll hear, I think, 3 r squareds in this class, r squared adjusted, r squared sub I, and r squared. R squared is the percent of variation in y explained by the variation in x's. 1,000 points for first person with this next definition. Next definition, get ready? R squared sub I is how the ith x in the model is explained by the other x's in the model. R squared sub I is how the ith x in the model is explained by the other x's in the model. So r squared sub I is about x being explained by x's. R squared sub I is how the, Amelia, fast typing right there, I love it. 3,000 points, yes, crazy points, Amelia, great job. So it's explained in Corbin, we're giving Corbin 1,000 there too, great job. Is how the ith x in the model is explained by the other x's in the model, exactly. So do you want your r squared sub I to be large or small? This is the counterintuitive thing. Do you want your r squared sub I to be large or small? Because this is how your x is explained by your other x's. Does that sound good or bad? Do you want your x's to explain your x? 100 points right there. I was good. Small. You don't want your x's to explain your x's. Let's throw a party here. You ready? We're going to throw a party, and we're going to have the awesomeness of the party. So we're going to have an equation here where the party is going to be awesome. So the y variable right here is how awesome the party is. Awesome. And so awesomeness is a score 1 through 10. So now we're going to have people bring some stuff to this party. You want your x's to explain? Yep. Who's going to bring something to the party right here? What are you guys going to bring to this party? I'm scared. I'm scared with these open-ended questions. What are you guys going to bring to this party? We'll have our y variable over here, which is our awesomeness. And let's throw in our x variables right here. Cups. We got cups. We got cups. So, yeah, it's multicollinear. Yes, Connor. Connor's in the chat knowing about some multicollinear. We got cookies. We got potato chips. Potato chips. That's it. Claw. You're only... There you go. You're $200. So, claw right here. We're talking about crab. Talking about crab brave claw. Red Bull. Connor, so good to have you, Connor. Is this it? Is that our whole party? Nothing more? Surely, it's Friday. We need more stuff at this party. You know what I'm going to do? We're just going to, you know what we're going to do? We're going to bring more cups. That's all. This is our party now. Everyone else is bringing cups. Now, do cups sound like a good idea at this party? Buffalo dip. Yeah, there we go. 100 points for bringing stuff to the party. Crab Rave Claw. Oh, man. They can't get us with... Wait, did not do it? Oh, did I do rainbow? What screen am I on? What is going on? Oh, no. Go away now. Okay. They can't get us for that. We got a copyright claim, but not a strike, Connor. So with all these cups at the party, our cups... No, we're just bringing cups, Philip. That's it. We can do extreme cups. Let's bring more cups. What does it look like is not needed at this party? So what does it look like is not needed at this party right now? So let's do this. Let's erase all those cups. But wait a minute. Don't we need some cups? Don't we need some cups? And maybe cups are only significant if we have drinks. We're actually talking about regression right here. Wouldn't you say cups are only significant if you have drinks? We only need cups. Think about this. Is the way regression works is that variables in the model, the way in which they're significant, are dependent on other variables. So now that we've got, let's bring some 2 liters right here. 2 liters. We should definitely have some cups. But you know what? How about if our model is just this? How does this sound like an awesome party now? Does this is oh cracking me up, man. Does this sound like 100 points, Philip, right there, making me laugh? Does this sound like an awesome party now? All we have is cups. That's it. Who wants to come to this cup stacking party? Is this good party? Yes or no? You guys are going to troll me and be like, totally awesome party. But think about this. This party now with just cups doesn't sound like an awesome party. Great party. I knew you guys would say it to me. But this party now with cookies, potato chips, all these things right here. Wait, how about let's bring some napkins now? We need some napkins. Would you agree that maybe napkins would be a good idea for this party? Who agrees that napkins is going to be a good idea for this party? Napkins, I think this would have a negative values. What would have negative coefficients on the awesomeness? So let's bring our loud friend. Loud friend. I'm not saying who anyone is. That's your loud friend. We're bringing they're gonna have a negative coefficient on the party. So just his friend was like, "Hey, what's up?" Is not against anybody here. They're the friend who is defined. Anyways. So right here, napkins is probably significant at this party now, but without the other variables, do you think napkins would be significant? Now, I can't stress this more than enough. It's that friend. How about this? Let's talk about friends a little bit more. Because F is for friends who do stuff together. U is for you and me. And it's for anywhere and anytime at all. You guys know what I'm talking about. So, with that, how about if your friend says, I'll drive you 1% of the way to New York? Is that a good friend, yes or no? Your friend says, I'll drive you 1% of the way to New York. So let's draw this map out. Oh, gosh. Brian's drawing time right here. Your friend says, I'll drive you 1% of the way to New York. Here's the United States. Here's tech. It's a bad friend. You guys are so mean. Awesome. There's the United States. That looks like an animal. So here's Tennessee. Oh, Tennessee's so easy to draw. Thank you, Tennessee. Here's New York. I don't know how to draw New York. And your friend says, I'll drive you 1% of the way to New York. Everyone's like, this is a bad friend right here. So I think New York's... So right here is Knoxville. There we go, Knoxville. And we're going to go to New York City. We're going to take a flight. And we're going to land right outside the city. And then our friend's going to pick us up at the airport and drive us the remaining 1%. Is that a bad friend? The friend who picks us up at the airport outside New York City and drives us the remaining 1% of the way, that's a bad friend? Really? But wait a minute. This friend right here is only significant in this model given what? They're only significant in the model given we have a flight. If that friend explains the 1% of the variation and gets us, so New York is 700 miles away, that's 7 miles. Yeah, they're going to get you they're going to pick you up at the airport, 7 miles away from their apartment. They're picking you up at the airport and they're driving you to their place. You could walk it. They could say, you know what? You said that 1% is not significant. Sure, you can walk from the airport to my place. It's only 7 miles. It's 1% of the way. So you can get your flight, and then once you get off the flight, you can walk the 7 miles with your bags. Or I can pick you up if it is significant, if that actually helps the model. You're like, okay, wait a minute, that is significant now. They're like, but it's only 1%. So, but what if we said that friend, which of these things is probably significant by itself? Would it be the flight is significant by itself, or your friend's variation is significant by itself? Which of those would be significant by itself? The flight, which I'm erasing now, or your friend? The flight is significant by itself. The flight by itself, like if you look at a model with just the flight would explain a significant amount of variation. If you look at a model with just your friend in it, that would not be significant. If you look at a model with your flight and the friend in it, then both the things would be significant. So the friend is only significant with the flight in it. This is the weird world of multiple regression. What can happen to the p-value of something in the model? It's something we always say. The p-value of something in the model can do what in a multiple regression? The p-value... Yeah, exactly, Sylvia, exactly. What can happen to the p-value of something in a multiple regression? The p-value, which maybe was significant, it could stay significant, or as we saw with weight, the p-value for weight in the simple regression, where's weight? Here's weight in the simple regression. Where did I lose it to? There's weight in the multiple, and we did it on the other page. And here is weight in the simple. I have to remake the model. Weight in the simple model, when we go here to just weight in the simple model, weight is significant, And then in the multiple world, weight is not significant. In the simple world, weight is significant. In the multiple world, it's not. But there's times where something is not significant, and in the multiple world, it is significant. Because maybe something like somebody's forearm, let's see here, is forearm not significant? Come on, forearm. You got this. Don't be significant. Oh, it is significant. So this is the weird world of multiple regression. And I'm going to explain how this kind of happens right now. You ready? A lot of what we have going on with the x's explaining the x's is when the x's explain the x's, they fight for what is significant. The best thing is if your x's bring with them new sources of variation. You want, when you're bringing a party, for everyone to bring something unique. Imagine if everyone's like, I'm going to bring Coke. You're like, oh, that's cool. And someone says, I'm going to bring Pepsi. What would you say to them? You'd be like, well, Coke's better, but we also already have soda. So if they're bringing Coke, but they're like, well, Pepsi's different. You're like, yeah, but it overlaps in the variation. And then one friend says, I'm bringing Pringles. Another friend says, I'm bringing Lay's. You're like, well, we already have the chip person. We already got the chips. You bring dip because that's new variation. And then dip is only significant if you have chips. So the significance of dip is dependent on chip. We're already talking about p-values again, that if one friend says, I'm bringing dip, and you're like, well, don't bring that. We don't have anyone bringing chips. Because dip is only significant in the model that has chips. So you can see how p-values are dependent on everything else in the model. Who thinks this is making sense? That the p-values in the model depend on what is in the model. If you have things that overlap, they'll fight each other, and they can't all be significant. Like they'll do the same thing, and you'll be like, okay, well, we can't use all these variables. If you have things that are unique, they do better. But if you have things that need other variables to work and you don't have them, maybe it won't be significant. So these are big, big things, and it all comes down to, and we'll be starting next class with this. Where's my VIF? It all comes down to this right here. This is the final topic, which we'll talk about for the last minute right here, is variance inflation factor. And the variance inflation factor is very easy to calculate. It's just a very simple formula using the r squared sub I. It's this. So variance inflation is 1 over 1 minus r squared of sub I. And what do you want your r squared sub I to be? What would be a really great r squared sub I? A really awesome r squared sub I would be what? 1,000 points, last answers. There's 2 last answers. Who's going to get them for our last few minutes class? What do you want your r squared sub I to be? What do you want your r squared, which is how your x's explain your other x's? 0, Brad, you're right. And then if it's 0, your VIF for that variable would be 1. Because if this is 0, it's 1 over 1. But as this goes closer to 1, you have higher variance inflation. Exactly. If you have higher variance inflation, that means that weight has other variables that overlap in the variation that it's bringing to the model. So weight is the variable here that has the most overlapping variation. And probably because of that, that's why weight was not significant, because weight overlaps in the variation that the other variables bring to the model. And it's called variance inflation. We're done. I can't really say much more. It's the square of the standard error. We've pretty much, so let me just say this. Chest probably has about 3 times because you just square root it. Knee probably has about 2 times the amount of uncertainty. Weight probably has between 5 and 6 because all you do to figure out how much our uncertainty has been increased is you just square root it. And that tells you about how much larger your uncertainty is because it's variance inflation factor. So variance is just standard error squared. So that's how you figure out how much more uncertainty you have due to the overlap between what the x's bring to the model. That's got it. Did that make sense? Sorry, I went like 30 seconds over right there. But does that make sense, everybody? Does everyone know what's going on right here with the variance inflation factor? It's impacted by the x's bringing the same sources of variation. So height is very unique. Ankle and height are very unique in what they bring. But I mean, ankle wasn't significant. It was just a bad variable overall. Forearm's pretty unique in what it brings to the model too. The smaller these numbers are, the better, because you're saying you're not increasing your uncertainty. If the variables overlap in what they bring, you have more uncertainty. That's got it. Everyone have a great weekend. So much stuff. Maybe I'll try to fix the camera here real quick. I don't know why. I don't know why it did this. Let me see. I'm gonna still exist, but I'm gonna vanish. Let me look. There's that. See if it's working.
Oh, that's the wrong
thing.
There's
right here.
I am
still here.
That's so weird.
Huh.
Change the
Change the
resolution
resolution on that.
Yeah,
Probably just like turn it off and on when we get back.
Flip
vertically.
Hello.
I'm still here.
I am just
trying to fix it.
Well, I didn't fix it, but I got the second one going right here. So all I did was change it over to the other one, copy my filters, so there we go. A little less pressure between classes. Like, what's going on? But got it fixed. So now, sorry, first class.
That has it back working. So we figured it out, or at least I was able to get this looking like this again. That is it. So it's like interesting when I pull this right here. You're like, oh, there you go. The magic of editing. So I will see everybody here shortly. Do we have audio on this screen? We should have audio. We do. I will see everyone here in just a little bit. Bye, everybody, for now. Bye. We get to see Crash twice right there. How's everyone doing this morning? There was an issue with the video this morning, but we got it fixed up. How is everybody doing? Everyone doing great? Everyone doing excellent. Morning, Hannah. How's everyone doing? Great. Awesome stuff right here. One of the biggest things I want to mention, so this is huge. This is the biggest thing. We will hop over. Let's go over to the main screen right here. The main screen right here. Let's take a quick look at this. This is not what we want to look at yet. But let's take a look at this right here. Let's go to data mining. And let's do data mining. R's crashing. It's one of the, whoa, look at all those files I got open. Big. Must. Test. Test. Are we fixed? So I was just echoing myself. I must have had... Is the stream? There we go. Sorry about that. Thank you, everyone. Big echo in the chat right away. Yep, there it is. Okay. I think we are good now. Oh, it's one of those mornings. Okay, we are good. Yes, I found the extra the audio source coming in. Wow, well, that's good. I got quick at fixing stuff really good. So yesterday, that's your wake up right there. That's your wake up. So yesterday, we were looking at the different models and explaining how to use them. We were looking at different models, looking at the differences right here with the naive, the all squared model, the data mining example, and we needed the comparison metric on how to compare the models. Every model, 100 points wake up question, 500 points. Every model was compared on the what for each model. Every single model had its what compared between models. We went from model to model to model to model. Every model had its what compared, ours being really just awkward today. What model, what is going to have it? We're comparing it to, hold on, 100 points right there. RMSE. We're going to look at the RMSEs for every model, and the RMSE is going to be compared to its holdout. We're going to look at the ratio here, and we want to figure out if these are bad. This one's not overfit because the way it works in new data, it just works bad. And we talked about the bias variance trade-off yesterday. Bias variance trade-off is something you need to know like that. You need to know bias variance trade-off, what it means. It's going to be a major component of the remainder of this class. Let's see. Computer work properly. Okay, we've got some slides to go through today. Let's take a look. Numeric prediction with linear regression. Now, the whole point of today is actually to do regression all over again. In 320, we take like 2.5 days to do this. But today, we're going to do regression again, but much quicker. So let's get ready to start doing regression again. Now, why are we doing linear regression again? Why am I teaching you linear regression? It's because it's like one of the most important things ever. It's literally like someone having a Swiss Army knife, and you'd be like, well, that's not the best tool. And they're like, but it's useful. We can use it all the time. It's not the best, but it's very, very useful. It's simple. It's easy to use. You're going to see a ton of people using simple regression or multiple regression, but it's one of the most powerful tools out there. So if you took 320, be ready to be like, okay, I got this. I've already done this before. So what do you need to know? How linear the models are. We need to make sure that we're actually fitting a linear model. We need to make sure that we put in squares of variables when appropriate. So sometimes we will actually need to square the variable if needed, and we need to be able to interpret the coefficient. Now, one thing I want to point out is we should have, let's go over to here. Let me go over to your class, and let's show you that there is a section on interpretation. Please go to this. I could go through and I could read off every interpretation, but please go to it, and please submit your midterm. Some people have. Make sure to submit your midterms. Let's go here to the modules, and I will show you where it's at, but there are slides directly on interpreting your coefficients. So under Data Mining 3, we see here contains interpretation help right here. So we'll pull this up real quick here. So I have these slides up and going. And these slides right here, let me show you them, have interpretation help right here. So these have all of the interpretation help. There are a lot fewer, but let's go here to 2. Otherwise, we should get to 2 otherwise. Here we are. There's so much interpretation that we can do, and we should be showing this all properly on the screen right here. But this is on Canvas right now, and it goes over how to interpret your coefficients. How to interpret coefficients is key right here. Make sure to reference these slides, and I will do this during class today, but we have key interpretations of what, there we go, classic, all models are wrong, some are useful. But your interpretations are listed right here with examples of how to interpret them. Please follow these, and I will be doing examples and explaining them, and you see multiple interpretations right here of how to interpret. So let's go back. We need to know, once again, are we doing models with just one variables, multiple variables? Are we squaring the coefficients? Are our models appropriate? That's the whole goal, is to make a model that's a reasonable reflection of reality. And all we're doing in simple linear regression is adding in one variable, and in multiple regression, we're adding in multiple variables. So if you're on what's the difference between simple and multiple? Simple is one variable, multiple is multiple variables. So now we need to evaluate our model. We need to make it and evaluate it. Let's do it. So classic right here. We've got the RMSE. What is the RMSE? The root, there's the root, of the mean of the squared errors. So all we're doing is taking the number of observations, and this is for a holdout to see how it's doing, and we're just dividing the error for what we have divided by how many observations there are. So this is the mean part of it, where we're taking the typical miss the model makes. And why are we squaring it? I love these theory questions. I wish I could just do a write your answer question. Why are we squaring it and not just taking the mean miss? What would we get if we got the mean miss of the model? Like if we took the miss of the model and the mean miss, what would the mean miss of the model be? No negatives, exactly, because the mean miss would be 0. Sarah, 100 points right there. The mean miss would be 0 if we just did the typical miss the model makes. We want to square everything and then add them all up and then divide by how many there are to get the mean miss the model makes, and then square root it to bring it back to the units of the problem. So literally let's make it very clear, the R and the S of this cancel out. So the R and the S of it cancel out. So down here, you can see what's also doing the work on it. Down here, 100 points first person in the chat. Thank you. 100 points all those people talking in the chat right now. That's what we want to see throughout class. What is doing the work of the R and the S heat? You have to tell me what this means. What is doing the work of the root and the square, which cancel, which get us the typical miss the model makes? Down here, it's because we're doing the what? Not, well, close, not average, because that's the mean and that's the error. It's going to be absolute value. Yep. Vedrina right there. Great job, Vedrina. So you are correct. It's the absolute. So instead of, this is just another way of doing it, you can do the root and the square to just figure out, all positive numbers, or you could just do absolute value. And you're like, well, which one's better? Just, if you square them, outliers have more of an impact. If you don't square them, outliers have less of an impact. Because think the most of this, when you talk about the squared error, most of the squared error is going to come from outliers because they're going to have a bigger squared error. So root mean squared error is going to be more sensitive to really bad outliers. So you have sensitivity in this one to outliers, where this one is not as sensitive outliers because you're not squaring the prediction, the error. You're not squaring the error. Here you're squaring it, so a squared error is going to be worse if you have a higher squared error. So which one's better? Do you want to weight your outliers more? Do you want to weight your outliers less? Preferences, and you shouldn't pick one because you think it looks good. You should kind of have a standard you use. Some people swear by MAE, some people swear by square. Some people swear by RMSE because it's squared. So that's what we have going on. Not that big of a difference. So why are they not the same? Just mechanically, mathematically, Jinning, 100 points, great question. Just because when you square it, well, because here we can do this right here. You ready? Let's do an example. Let's hop over to the other screen here. My screens are being weird. Desktop. Good. Okay. So if we do an example, everything's going crazy. So if we do an example where we have points like, let's do this, let's go numbers. And numbers are going to be 1, 4, 10, and 100. Okay. So now what we're going to do is we're going to take the mean of these numbers. So we're going to take the mean of numbers. And the mean of the numbers is that. So to find out the root mean squared error, we have to go and we have to do numbers minus the mean of the numbers. So this is the error. Every number is off from it. So let's just call this the error term right here. Does this make sense that this is the error term for these numbers? It's how far away every number is from the error. So if we're doing mean absolute error, we'd go here to mean ABS error. So that's mean absolute error. But now think about when you square these numbers, which of these will have the biggest impact? This is going to be a big, big number. That's going to take over a lot of the root, so square root, mean squared error. So here's the mathematics for the root mean squared error. And especially if we were to do something crazy right here, like 1,000, then you're going to see even bigger differences, kind of. It's interesting mathematically how that works. So you'll notice that there is a difference, and it's just mathematically how you're going to get these differences right here. Like here's the root mean squared error, and here's the mean absolute error. So what you notice here is just mathematically they're different. Does that help make sense a little bit? How we calculate the mean absolute error versus the root mean squared error. So this, and you can see root mean squared error, mean absolute error, and yeah. So just the mathematics is, yeah, it's a good question, great question. Why are my transitions? Okay. So with this right here, what do we have going on? So we got R squared and R squared of justice. They're like moments, different powers, give different errors. Yeah, exactly. Nin, great job, Nin, 100 points right there. R squared is the percent of variation in Y explained by the variation in X's. R squared adjusted is going to be adjusted for how many variables are in the model. But we're focusing on predictive analytics right here, so our goal is not like how the model does by itself. Our whole goal here is to see how it does on a holdout, and we're going to use our k-fold cross-validation process to make estimates of how it will do on the holdout. So we're going to use the k-fold cross-validation process to estimate how this model does on the holdout. So we've got, how does the model do on the data it was created from? How do we estimate the model will do? And how does the model do on new data? 3 key steps that we should know really well. We've been covering it a lot this week. How does the model do on the data it's created from? Training. How do we think it'll do on new data? Validation. How does it actually do on new data? Holdout. Huge. Which is the holdout is how the model generalizes. If it generalizes well, the holdout should have an error that is less than what more than the validation? It should be within what percent of the validation? 100 points first person right here. The holdout should have an error within what percent of the validation? And this is kind of our general metric. 10%, Anisha, great job. Within 10%, because that's like pretty good. You might use a standard of 25, but the notes say 10. You're like, why 10? It's just one of those numbers. 100 points, everyone. Thank you, everyone listening in. Make sure you're following along, because that's the number we'll use. Could you use 12? I mean, there's no magic number. It's just a general guideline. So the naive model, this is huge. The naive model is the no variable model. So the naive model is a very easy model to make. Here, I'll put R on the screen in a smaller window. The naive model, stop being crazy R today. There you go. The naive model is a model that does not have any variables in it. I've already got some data loaded up here. I'm going to load it again. Never hurts. And we're going to go right here to lm height tilde 1 comma datas equals survey 10. Let's do a summary of our model, and all the naive model has in it is going to be just the intercept. All the naive model has in it is the intercept. If you look right here, it's the intercept, which is just the value of y at all points. The naive model looks like a flat line in the linear model. It predicts the same value of y no matter what x is, because there's no x's. So there's no x to explain. It's the same value of y consistently throughout the model. So the naive model is going to be like our jumping off point. There's no predictors in the naive model. It's going to predict the mean of y, the average value of y observed in the training data. So the training data makes the naive model. And you can see right here, we're going to make a naive model right here. You can just store the mean of y. There you go. That's another way to make it. Just take the mean from the training. Boom. Right here in code. Store it as your naive model. And this would predict at all points. So you could use the holdout from profit, which is going to be the values of profit in your holdout. Does everyone understand right here? This is your y data from the new values. This is within the holdout data set. We want to predict profit. So this would be a vector of values. And we're going to subtract from it the naive model. And what does this look like? This code looks just like what we were doing over here in just a second, right here. This code is the exact same thing we were doing where we were getting the error, and I can make it a little more clear if I take the error as is, and I go here and replace the error with this. So all I'm doing is taking my prediction or my actual values, the actual numbers, subtracting off what the naive model was, and then I'm doing this right here. So this is virtually identical to what you have right here with the root mean squared error. So very important, we can see what's going on right here, that we're just finding how does the naive model do on new data. The naive model is made from the holdout, the training, or the validation. The naive model is made from the holdout, the training, or the validation. What makes the naive model? Easy test questions. What makes it 100 points first person? What makes the naive model? Holdout, training, or validation? Training, Sarah, great job right there. It's training. Training makes the naive model. The holdout is where we test our model. The validation is how we select our model. So the training, the training will make the naive model. The mean, if you look right here, the average value of y observed in the training data. Good job right there. Practice, practice, practice. We got this. Like, you'll remember them on the test. Like, I want to say this. First off, great job on the test. I think the average was like an 85. I know the take-home's going to be tougher. Might be a curve on the take-home. So there's no curve on the actual test, or at least what exactly is the training? It's the data that makes the model. The training makes the model. The validation is how we select the model. And then from all the models. So the training will make all the different models. The naive is just one of the many models we can make from the training. Maybe we'll select the naive, but the naive has very high bias. It has very low variance, which is good, but it does a very bad job. So the training makes different models for us, or the model will be made from training, but we'll make a ton of models. The validation is how we select the models from the training. And then the holdout is how we test if it'll work. Like we give the final test on the holdout. So we do one sort of test on the holdout. Does that process make sense, Madeline? Is like you're going to use the training to make a bunch of models. Then you're going to look at the validation to see which model to select. And then on the holdout, you're going to see if your model actually works. So that's the process. Very important process we do in predictive analytics. So if you don't know that process, you're probably going to fail the final. And also, I do want to say about the midterm, excellent work. So I was saying that a lot of great grades on the midterm. I think there was 2 100s. Very impressed by that. No one got 100 on the 320, but 2 people got hundreds on the 474. And what really makes me feel good is I use some questions because we do a review of 320 and 474, and I want to look at the item analysis of that. But the fact that 474 was just doing, I'm very proud of everyone. I'm proud of 320 also, but I'm glad in 474 we saw what looks to be on the questions that are like understanding how to code better grades, which is what should happen. Like this is your second time coding. So if I give you coding questions, you should be more proficient in it. We should also give 320 some like, okay, when I'm doing this in 474, I'm going to do even better. Because we don't want to give you just a slight understanding of coding. We want to make sure you have that really good, solid foundation. If you've ever taken a class, you see I'm old. Yeah, great job. I'm very proud of 320 also. You guys have the harder take home. You guys have the easier test, maybe harder take home. See, would you change that over? Would you rather have the easier take home? Because some of them are saying they got the take home done in like an hour or 2 hours, which you guys are probably like, ha 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 ha. I'd love that. But your guys' test I think was easier. Like looking at the grades, but better performance. Maybe you guys are just doing better. Yeah. So you know, I'm trying to keep everything of even difficulty. You know, it's 2 different classes. So, but I am very proud of both classes. 320 did quite well. They still did well. It wasn't the scenario, if you heard me talk about this, where the first time I gave an online test, yeah, their take homes like a bit easier, but their test was a little bit lower, so maybe their test was a little bit harder for their skill level. So it all depends. Now, please be working on your take home. It is due tonight, and Brian is probably traveling or something this weekend and everything. So please be working on your take home. Please be working on your take home. Please, 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 please work on your take home. So let's talk about the linear regression model and assumptions. So what do we have right here? The model is simply, and this is why people drive me nuts, because remember when the fire alarm went off? Oh yeah, I do remember that. That was crazy. And it's been so crazy. I don't want craziness, but man, we've experienced so much craziness. People really love some y equals mx plus b. And you know what? I liked it too, till I started doing stats. Because y equals mx plus b is limited in what you can put into it. Y hat equals b0 plus b1x1 plus b2x2 ... as many as we ever want to put into it, up to b, k, and Burger King xk. Now, these are subscripts right here, meaning the coefficient of the first x, the second x with its coefficient, and this is the intercept now, which is relative to, yeah, that one. So I even have to think, because I don't use the general notation. Nitin, how do they do notation for higher order models in algebra and stuff like that? When, like, what is the proper notation beyond y equals mx plus b? What do they start doing in mathematics? I am actually very interested, but I just don't do mathematics. I do statistics. So if you notice right here, we have the same equation here as is here. This is it? Like, no, what we're doing right here? So why do they even do y equals mx plus b? Why do we learn y equals? Why doesn't they need to change this? They need to fix this. And coefficient linear model. So do they is it different letters? Is it like is it b? Is it? I should be able to take a guess at this. Looking at the, is it y equals? You should put the b first. Is it m1x1? Yeah, and is it like plus m2x2? Is that how it looks, or am I just going crazy? I mean, it makes more sense to me to put the b first, because the order of the polynomials, or it doesn't have an x on it. I guess x would be to the 0, because there's no x. You raise x to 0, it's 1. So and so if you look, it's just a reordering. Hopefully that makes sense to everybody. I like it better. Yeah. I guess y equals mx plus b, but that's what people are constantly, it's what we learn. I mean, it's all right. I mean, but it'd be harder to do that with this right here. So if you look, all we have is multiple variables. And then the biggest problem right here with this, we have our x's, we have the coefficients. Just think of the coefficients as a weight, like how much it's going to impact the model. So the coefficients up here are just the weights of how much that variable kind of impacts whatever we're trying to predict. We're trying to predict y, and the coefficient of y is going, not the coefficient of y, excuse me. The coefficient is going to impact y based on its weight. Now, one of the hardest things is figuring out like what sort of a relationship x and y have. And I don't know if we have the Kaggle slides on here anymore. I wish we did. But in this Kaggle competition, somebody won like $10,000 because they figured out a combination of the x's that explained like 98% of the variation. So they were able to like be like, oh, this specific like log transformation ratio of these 3 values like figures out 98% of the variation. And it's like, how in the world would you figure this out? And it's just people like Zach winning all the Kaggles. It's like, you got secret code that you didn't share. So with all this right here, we've also got predictors can be indicator variables defined as categorical variables. So, you know, I tell you in 201 QQ straight enough, no outliers, plot doesn't thicken. But then when you get to 320 and 474, you learn that you can use categorical variables. And it's actually pretty easy to see and do. Let's see if the main screen hops over here. Let's go over to the main screen. And let's look at a little QQ straight enough, no outliers, without that actually working. So QQ straight enough, no outliers. What am I talking about? QQ means both variables are quantitative, but watch this. I'm going to predict somebody's height based on their weight and their GPA. Now, oh, not GPA, we'll go gender. And so now, good, that's fine. We're going to go here to visualize model. And you say, wait a minute, gender is categorical. I say, I know. Because now when I visualize my model, I get the following. Computer. So we visualize the model. Magic. R is just being very odd today. We had all these tech issues this morning. If you notice right here, we get a model with indicator variable. We get a line for females and a line for males right here. We can even do crazier things. We can include interactions, which we'll show today. But now here's an interaction model between the two. Oh, because the p-value is so... Let's do GPA. There we go. There's an interaction that's significant, or more, but not enough. So this right here has a little bit more of a significant interaction, and we see a difference between the lines. R just said no. Really? There was tech issues with the camera this morning and everything, but if you notice here, we see differences between the lines. And so what did Brian include in this model? We included in this model right here. R is just being so odd. GPA is the Y variable, weight is an X, and gender is an X, and we're including the interaction between these two variables. And let's go ahead and look at the summary of this model right here. The summary of the model is going to show that we have significant, anything significant? There we go. Let's rerun the summary here again. And here we are. We've got weight is significant in the model, but nothing else is significant. Now, that's not that big of a deal. We'll talk more about whether or not things should be significant, but our goal here is not to make a model that describes data, but to make a predictive model. So we wouldn't care how well this model works and its coefficients. Our whole goal here with this model is to get the smallest what. What is our primary goal? 100 points first person. What is our primary goal with this model? How will these models be evaluated on how they're doing? Who you should be able to, because I'm not going to really care about these p-values anymore. P-values are like, whatever, p-values. RMSE, boom, and RMSE on holdout. Sarah and Jordan right there, 100 points. And Nitin, error, you're right. Smallest error. We're going to focus in on this RMSE. That's going to be what we're going to focus. Because you're like, well, I don't care about the p-values. I mean, I kind of do. I want things to be significant in the model, but it's like, if they're not significant, so what? We're going to care about that RMSE. That's what we're caring about in predictive analytics. That is how we are going to measure. Okay. So with these coefficients right here, the X predictors, all this good stuff, big slide right there. All models are wrong. Some are useful. I can't state this enough, that you're never going to find this perfect model. It's a dream. What's a good and a bad RMSE? Context. Imagine this, Sarah, 100 points, great question. I can predict how many wins your team will get, and I'm usually off by about 6 wins. Is that good or bad? I'm going to predict how many wins your team will get, and I'm typically off, because that's what an RMSE is. When I make predictions, I'm typically off by about 6 wins. RMSE is typical miss, so when I make predictions, I'm typically off by about 6 wins. Is that good or bad? 500 points, first person who says what I want you to be saying for this when I say that. Is 6 wins good or bad? 100 points, Phaedron right there. So there's something I want you to say, though. I can give away the answer if it's a trick question. It's a trick question. Nin's right, can't say. Because what if it's, what did I say, 5 wins? What if it's 5 wins I'm typically off by predicting football? Carolyn, right? You're right. What if it's football? If I'm typically off by how many wins your team gets in a season in football, that's a big amount. But what if it's baseball? Baseball has like 162 games. In baseball, if I can predict how many wins your team will get in a season in baseball, and I'm typically off by about 5, that's amazing. In baseball, you'd be like, you can predict within 5, like usually within 5 wins. Like typically, it doesn't mean you'll be off by 5. It means when I make predictions, yep. So it all depends. I used the baseball football example yesterday, maybe, but it depends on the context. So when is an RMSE good? you just have to look at it and be like, well, we're typically off by this amount. Like, imagine if you're trying to predict people's monthly Kroger amount they buy at Kroger each month, and you're typically off by about $100. That might be all right. That might be all right. It'd be better if it was yearly amount. Like, if you're predicting how much people spend yearly at Kroger and you're typically off by 100, that'd be better because a year's a lot more time. And if you're only off by about 100 over a year in what people spend in Kroger, that'd be much better. If it's daily and you're off by 100, you're like, what kind of model are you making that you were off by about 100 on what people spend daily at Kroger? Like, that model, you see at each point, it was 100. So all these models are wrong, but the one that's most useful is probably the one that's predicting yearly spending on Kroger that's typically off by about 100. Now, you might want monthly spending, so hopefully you could make a monthly spending model and it would have a good, like, whatever you want to analyze. But yes, equations are not physical laws. We can't say that if people spend, or like if people have a salary of this and it increases by $1, they will spend this much more at Kroger. Do not say that. Do not say that, because we would say two people who differ in their salary by $100 are expected to differ in how much they spend at Kroger by, and then we'd give the coefficient. So we would not say something like, oh, if you get $100 more, you will spend this much more at Kroger. It's just what we expect given the model. Models do not say what will happen. They just say what we expect or what we would predict. Could this model be helpful to somebody? This model right here, could this be helpful, yes or no? The red line is the model. It's trying to explain these black dots. Do you think this model could be pretty good? Pretty helpful? Yes. Adrian, 100 points right there. This model could be pretty good. But how wrong is this model? This model is extremely wrong. This is the perfect example of this red line is wrong, but it explains a lot of the variation. It's the wrong polynomial degree, because there should fit a second order because we got this bend. But this model is so wrong, but it's so useful. So this model explains maybe 98% of the variation. And so you could look at this right here, and actually we could figure out, it should be pretty easy to jump into R right here. Let me go to the small window. Everything's being crazy today. R just keeps crashing when I change the window size. So we go right here. Here, we'll just run it. Cool. And there's the values. So we have the X, we have the Y, and let's go M save into LM Y tilde X. It should do it. It does. And then let's go summary. The R squared on that is 90. What did I say? 98%. The R squared on that is 97%. As in 97% of the variation in these black dots is explained by the line. So you could, here's the thing then, is you could easily go right here and you could add in the polynomial term to this. So all we're going to do now is go right here. R keeps doing the not responding thing. You couldn't see in the corner. And we're going to go here, add in the polynomial term. And now, do we not get it? Was it not giving the coefficients for it? Wait. Oh, wait. What is going on? R squared. Did not do it. X squared. X and X squared. Oh, did it fit the non-polynomial? Random uniform X's and Y equals the squared. My brain's just not. 96. Let me full screen this, see what's going on right here. Let's look. Let's make a second model right here. Let's make a second model. Model 1, Model 2, Model 1, Model 2. Let's do X times X. It's not putting in the second X. And is it, oh, is it not because it doesn't have enough values? Can we not do a polynomial on this? Choose. This is like, see there, see the not responding? You saw it for a second. You saw it. Choose order. We still have the other model stored, right? Yeah, so really it doesn't want to do that. As I thought, it would explain 100% of the variation. So it's being really weird. It's saying like, no, I won't make that model for you. And I think there's some sort of a collinearity problem or something. But see, look, you see it. Really, ours being, we're going to try reinstalling some stuff this weekend. But we were having all the tech issues this morning. No. Okay. So as we thought, the polynomial model would explain 100% of the variation, and that's what we have going. You know what I think? Oh, I think maybe you can't do that outside of data frames. Maybe it's because it's outside of a data frame, it wouldn't. Exactly. I broke it. So it's outside of a data frame. Maybe that's the issue on why it wouldn't square it for me. But I did confirm, if you saw the graphic in the corner, that it is working 100%. It is like 100% of the variation is explained by the polynomial. Because you can look, it is a polynomial model making it. It is a polynomial model making it right here. So 100% of the variation would be explained by the polynomial model. So here we are with a multiple regression model, and we see some interpretation on the slide. Now, this is key right here. Whenever you see a variable in a multiple model, you must focus in on what is the variable type. This slide is where we have to pause for a moment, because every single thing on here, you should know what it means. Get ready to take some big notes. Here we go. All of these estimates are all what's. All of these estimates are what's in the equations. All of these estimates, 100 points first person, are all the what's that you saw here previously in the equation. All of those estimates are all the coefficients. Sarah right there, 100 points. That's all the B's. So they're all the estimates. And one of them is the intercept. This is the intercept, which is B0, and these are all the B1s. And when you write the equation, which I can't do written tests, when you write the equation, you would do B0, and then it's not times by anything because it's just the intercept, plus B1, 100 points. Thank you for all those people responding. B1 plus B1 times X1 plus B2 times X2 plus B3 times X3. Do you see how you just go through here, and writing the equation is literally just taking this, intercept is not times by anything, plus this times this, plus this times this, plus this times this. You just go through and do this, and you would write out the equation, which is the same thing as we have right here. It's just intercept this plus this times this, plus this times this, plus this times this, plus this times this. And you just go through and you write it just like it just takes a while. Just go. Does that make sense? That took me the longest time to realize that's all you do with that part of the output. It's just your estimates and your X values. So we got that part down. Now, what are your standard errors? We don't have to go too in-depth on standard errors in this class, but standard errors are your uncertainty. It's like your friend saying to you, I'll give you $20, but I could be off by about $2.36. This friend said, I'll give you 28 cents, but they might be off by about 5 cents. Now I am using the pause. I'll give you negative 28 cents. But look at these. I'll give you 45 cents, but I could be off by about 80 cents. So all of a sudden now there's more uncertainty than even the estimate. Does everyone notice that if you divide 40 by 80, what do you get? 40 or negative 40 by 80 is what? 40 divided by 80 is what? I know I'm rounding them very sharply, but 40 divided by 80 is what? 40 divided by 80. 1/2 negative, and that's what this is. This number right here, let me do it this way. This number right here are these two numbers divided, and you divide them in this order. So you can look at any one of these values right here and see how it's calculated, that if you were to take this number right here, there we go, this number right here is merely these two numbers divided. Does that make sense? That to get the t statistic, the t value, it's just a ratio of what your estimate is to your standard error. So all you're doing is standardizing it. It's literally just like a z-score, literally just like it. And there's a good question from Sarah right there. How is RMSE different from standard error? Your RMSE is right down here. This is your RMSE, which RMSE is your uncertainty in the residuals. So RMSE is like your typical miss about how far off the residuals might be. And so it's your uncertainty in the residuals. This standard error is your uncertainty in your estimate of the coefficient. So take a look right here. This is your standard error on this estimate. Where down here, the RMSE, which is down here, is your uncertainty in your residual estimate, like how far off the residuals might be. This is about how far off you might be when you estimate this quantity. So if you think of standard error as just uncertainty, this is my uncertainty in the estimate of these coefficients. This is my uncertainty in how far off the residuals might be. Does that make sense right there? That standard error is just uncertainty, and then you have to look at what it's the standard error for. This is my uncertainty in the estimates right here. So each one is relative to each estimate, how uncertain you are of that estimate. Do you want your standard errors to be large or small? What would you like your standard errors to be? Standard errors are really good when they're really what? You want standard errors. RMSE is the uncertainty. So, yes, RMSE, yes. RMSE is the uncertainty of the model's residuals estimates, yeah. And RMSE is root mean squared error. So this right here is root mean square error. That is the root mean square error in the output. And you want them to be small. Less uncertainty is better. Don't worry about the degrees of freedom. I mean, it's used for the F and the chi-squared and all that good stuff. But we don't use it in this class because it's just a calculation background thing. I mean, it's important, but you won't interpret it in the business world. Multiple R squared is the percent of variation Y explained by the variation in X. So that's the percent of variation we're explaining in one, like in our Y variable, due to the variation in our X's. So you want R squared to be higher. The higher the R squared, the better. It's always good right there. Mean minus value equals residual. Yes, residual equals actual minus predicted. So I like to say residual wrap. So residual equals actual minus predicted. So it's the error the model makes. So I always say residual wrap, just like wrap. Residual equals actual minus predicted, and that's the way I keep it straight in my head. When we were doing it before to get a residual, the predicted was the mean of the model. So when I was using the naive model and I was doing the mean, that's because the naive model was making the prediction. Does that make sense, Nitin? If you look at the output we had before, it was like the Y value minus the mean. So the Y value was the actual value because it's the actual value of what we're trying to understand. And then we were subtracting off the mean because the mean was the predicted. Multiple R squared is always higher than R squared adjusted. 100 points, Caroline, right there. Because R squared adjusted is a R squared with a penalty term. Remember, in some 320 right there. Excellent work. R squared, multiple R squared will always be higher than R squared adjusted. I think there's the odd circumstance that if it's 1, they'll both be 1. But it's R squared with a penalty term. And saying it's always lower, I'm totally fine with that because there's like always that one. Don't worry. I'm not going to do a trick question on the test like that. I stand by that R squared adjusted is always lower than R squared because it's R squared with a penalty term. And we could look at the equation because I think there's like, if R squared, I'm going to do it just for the heck of it. I think if R squared is 1, R squared adjusted is also 1. R squared adjusted equation. Because I'm not going to put this as a test question because even I'm like, I think. Yeah, it'll be 1. I'll show you. The only instance where it would not follow this rule, because here's the equation. The only way you break the rule and they're the same is when so here's how R squared adjusted is computed, and the only time it breaks the rules is if R squared, your original R squared is 1, because then you'd get 1 minus 1, that'd be 0, and then you get 0 times this is 0, and it'd be 1 minus 0, so your R squared adjusted would be 1. So only in that rare circumstance, which maybe that'll be a bonus question, but only in that one theoretical circumstance could R squared and R squared adjusted be the same. So in all other instances, R squared adjusted is always lower. But if you get an R squared of 1, you'll be like, R squared's 1? What? So pretty interesting stuff. And we might have had that in our output. What? It's showing the graphic now. Kara, you behave? Yeah, see the R squared adjusteds here are 1. You can't see it though. R not behaving. The R squared adjusteds are 1 right here. So that's because the R squareds are 1. So, and I was kind of thinking back on that. So much theory. I don't expect you to know the theory that deep, but it's good questions. I like it a lot. And here's our F statistic, which is how much more variation we observe being explained than we would have expected via random chance. Not that big of a deal. Here's the p-value for the overall model. Once again, this is not going to be our key aspect of focus. The most important, you know what? I love this type of question. What is the most important number in this output for predictive analytics? What is the most important for our class in predictive analytics? Imagine this is a test question. It said, for our class in predictive analytics, please enter the most important number. There's another one you could use, but we're going to go by what we're standard going on. Oh, careful. Yep. RMSE. Yep, that's the key focus. The typical miss the model makes. So the RMSE is what we want to look at. So we'd want to go boom to that RMSE. So if you saw this, you'd be like, oh, we need the RMSE. And then knowing that this is the RMSE, the p-value is just the significand of each variable in the model. Good stuff there. And I love it. And so good answers is practice. We like it. And here's something I want to point out. Bill is a quantitative variable. Bill is a quantitative variable. Gender male is an indicator variable. Gender male is an indicator variable, and the reference level is female. These days right here are going to be indicator variables where the reference level is Saturday. So it's key to understand that when we compare 2 days, and this is in the interpretations, this right here, let me interpret this. So this is in the video now too, so you can hear me say it. 2 days that are otherwise identical, where one day is a Saturday and the other day is a wait a minute. Oh, it was 0. Wait. Oh, it's Friday. Good. I was very confused. Sorry, reading that got me confused. So the only day missing here is Friday. We can confirm this also by looking at it. Friday is the reference level because it comes first. So reference levels are first. I am first for indicator reference levels. So 2 days that are otherwise identical, where one day is a Saturday and the other day is a Friday. The day in which is a Saturday is expected to have a tip percentage, because we're predicting tip percentage in this model, that is negative, that is 0.31% lower, because we're predicting tip percentage in percent of tip. So 2 days, let's do Sunday right here. 2 days that are otherwise identical, where one day is a Sunday and the other day is a Friday. The day in which it is a Sunday is expected to have a tip percentage that is 1.458% higher. Now, please use what I'm saying right here. Come back to this video to this part when you're interpreting, because you have to say 2 days that are otherwise identical. And I want to make this as clear as possible by showing you an example that'll make it very clear what we say why are otherwise identical. Let's hop over back to the main screen. Everything will work. R will expand. Yes. Okay, so what I'm going to do right here is I'm going to use a body fat data set. So let's go to body fat, and we're going to predict from somebody's, let's predict somebody's body fat. Is it lowercase body fat? I was doing this earlier today. R is just crashy. The problems compounded this week. It was like where I had little problems, and now it's just getting like, R is not responding. It was like the camera this morning was just going crazy. Everything was going crazy. It's a Friday. We're on hard mode right now. This is the final boss. Body fat, tilde. It's because we can see there how to spell it. Snowball effect, you got it. And so I want you to think about this. This is a multiple regression model. And so with this multiple regression model, we're predicting somebody's body fat. And I want you to think about this. The coefficient of weight here is what? We're predicting someone's body fat. What's odd about this coefficient of weight when we predict someone's body fat? The coefficient of somebody's weight here is actually what? The coefficient of weight is actually, I know, I'm so excited it's Friday. The coefficient of somebody's weight is oddly what right here? It's negative. So we're predicting body fat. Remember that? We're predicting body fat if R wants to behave. So we're predicting body fat, and we have a negative coefficient of weight. But when you think about the multiple world right here, what does this mean? Two people who are otherwise identical, who differ in their body fat, or excuse me, two people who are otherwise identical, who differ in their weight by 1 pound. The person who weighs more is expected to have a lower body fat by 0.08%. And it's percent because it's in body fat. You always interpret in units of the Y. If we're predicting like height, we would say inches taller or shorter. Now, we're not saying they will have lower body fat, but think about this. If two people are identical, they'd have the same age, the same height, the same neck measurement, the same chest measurement, same abdomen, same hip, same thigh, same ankle, same bicep, same forearm, same wrist. Everything is otherwise identical about them. And let's say there's another Brian, but that Brian weighs 30 pounds more. That Brian weighs 30 pounds more, and we'd expect that identical Brian, all the same measurements as this Brian, but he weighs 30 pounds more. We'd expect that identical Brian to, let's figure it out mathematically. We can take this coefficient. We'd expect that identical Brian right here to have, he weighs 30 pounds more, his fat would be 2.4% lower. Why is that? How could this person, well, but no, he'd have 2.4% less body fat, just so you can see it would be negative. The coefficient's technically negative. Why would he have less body fat if he weighs more? Why would we predict to an identical person to Brian who has more weight, but he's identical, he has the same chest measurements, Adam, 100 points, and then right there, 100 points too, more muscle, because he has all the same measurements. We're not saying he has more muscle, But how could you keep every measurement identical but gain weight? So imagine if someone's like, I've gained 20 pounds, but I'm still the same size. Would you be like, you'd have to be more compact, and muscle weighs more than fat. So this is why we have to add in two otherwise identical individuals where they differ in their weight by 1 pound are expected to differ in their body fat by negative 0.08, where the person who weighs more is expected to have less body fat. But here's the confusing thing, and please, I'm going to put this on your guys' test, and I want to see even better than 320. So you guys have things from 320. Here's the interpretation you don't want to do. This is a simple model right here. It's just predicting. And if you notice now, the coefficient is now positive. So now in this model, two individuals who differ in their weight by 1 pound, I don't have to say otherwise identical because it's not a multiple, are expected to differ in their body fat by 0.16%, where the person who weighs more is expected to have a higher body fat. But do not, whatever you do not do the following. Do not do this. This is one of my favorite examples to do. Do not do this, because if you were to do this, let's interpret what this means right here. Got everything typed in. There we go. I'm that quick. I'm instant transmission typing. So now, two individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the person who weighs more is expected to be taller. Do you know how many times I've gone over these interpretations right here? Like, I'm being very specific, and you need to be very exact in your interpretations. So if you are interpreting things on your homework assignments, come to this part of the video. Make sure it sounds accurate, because do you know what a bad interpretation is? For each pound you gain, your weight will increase. For each pound you gain, your height will increase by 0.07 inches. So I'm going to make some cheeseburgers this weekend. That's the plan. If I want to get taller, I want to be in the NBA. What should I do if I want to be in the NBA according to the interpretation? For each additional pound you gain, your height increases by 0.07 inches. How many of those cheeseburgers should I eat? I want to be in the NBA. It's my dream. I never told anyone that dream, but it's the dream to be in the NBA. Bulk up. Just keep eating the cheeseburgers. Cheeseburgers in paradise. 100 points everywhere there. A bunch. Because it just doesn't... Just think about this for a moment. You're saying that if you gain weight, you will get taller? No. That's the wrong interpretation. It's two people, which is the right interpretation, two people who differ in their weight by 1 pound. We expect the person who weighs more to be 0.07 inches taller. It's generally like, well, generally people who weigh more are taller. Now, that's not saying they will be. So don't say they will be taller. Say we would expect them to be. Please notice these are keywords that I can put on the test that are so small, but change everything dramatically. Listen to the difference. Two people who differ in their weight by 1 pound will differ in their height by 0.07 inches. That sounds like a physical law. Two people who differ in their weight by 1 pound are expected, sounds like we're making predictions now, are expected to differ in their weight by 0.07 inches. That small change, which someone could be like, it's just will and expect. One is saying this will happen. The other is saying I predict or expect this to happen. So it's so key to understand that. So please, please, please don't make those mistakes. Don't do it. Don't do it. Switching back to the main screen. Come on, you can do it. There it goes. Wait. Okay. So let's take a look right here. So we've got here the coefficient of Bill by itself. Cool, cool, cool. The coefficient of smoker. You'll see there's interpretations on this right here. The difference in the tip right here between people who are smokers yes and smokers no is expected to be this. And this, I want to make this very, very clear. This is only percentage because it's in respect to the what variable of this model. Give me the notation, 100 points. What units do we talk about the difference of this coefficient being in? The units are in the units of the what variable of the model. Whenever we talk about this, whenever we talk about its units, it needs to be in the units of the what. Whenever you're talking about like, oh, two individuals where one is, units of y, 100 points. Jordan right there, you're totally right. That's the units of the y. If you notice, when I was interpreting the coefficient of weight is not in units of pounds. The coefficient of weight was in units of inches and feet because we're interpreting the coefficient of weight predicting height. This is the coefficient of somebody being a smoker, yes, when we're predicting tip percentage. So tip percentage is in percent, so it's a percentage, only by virtue of tip percentage being percent. A lot of people will put the percentage because maybe the notes have it. Only do it when your Y is in percentage. Don't just put percentage. It's units of the Y. If you notice right here, we just have the differences between the different levels of weekday, and every weekday right here is compared to Friday. Why is every weekday compared to Friday? Because Friday is the first day alphabetically. So whenever you have indicator levels, they are all compared to Friday, at least in this instance, the first level alphabetical. So if you look at things like smoker, where is smoker no? Smoker no is what we call the reference level. So smoker no is the reference level here. And then for this problem, the reference level is what? Really good question. I could put day of the week on there. So imagine this question on the test. The reference level for day of the week is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Which one of those? Friday, because it comes first alphabetical. Huge note you should have. Reference levels are the first alphabetical level. So please take that note. That's such an easy test question for me to write. I wish Alex was in this class. He puts down a lot of my test questions, but that's such an easy test question. Like, what's the reference level for day of the week? It's Friday because it's first alphabetical. What is the reference level for freshman, sophomore, junior, senior? What's the reference level for freshman, sophomore, junior, senior? What is the reference level for freshman, sophomore, junior, senior? Which that one, I don't like this one a lot because, yeah, it's freshman, and it's because it's first alphabetical. So, and I was like, well, freshman's first, but it's not because it comes first. It's first alphabetical. So it would be freshman, and so that one's kind of got where you can get it right, but not because you knew it. I like day of the week even better because some people might be like, it's Monday because it comes first. I think Monday should be the first day of the week. It makes more sense. The weekend is Saturday, Sunday. Monday's the first day of the week. So we'll be like, it's Sunday because that's what America decided. Monday, it should be Monday. At least personal opinion here. I know, right? It should be Monday. And so it's the weekend. It's not the week start beginning or start end. I don't know. And so it's Friday, though, is the indicator, is the reference level. I think it's weird that we have names for the days. Yeah, a lot of them are from like the Greek and stuff like that. Like Thor's, like Thor's Day. And there's other days too. And then lunes, martes, miércoles, jueves. Oh my gosh, I forget the day of the week. Lunes, martes, miércoles, jueves, sábado, domingo. I forgot a day. Viernes. Viernes? Friday? I'm done. So, Viernes. Yeah, there we go. So, it's today. How do I not know what day today is? But lunes sounds like sun, like lunar. So there's a lot, especially between languages. It's really kind of cool to look at the different things like between the languages. And yeah, I like it. So I think it goes back to like Greek and Roman times. So TGI. I like that, TGIV. I like that a lot. So we've got here we talked about these things in the output. We know what's going on. That's what they are. So make sure you know. We talked about them in the output. The slides tell you too. Interactions. Whew. Interactions. There's something else. So when it comes to interactions, we can get tons and 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 tons of interactions. So when you look at something with 100 variables, there would be 4,950 interactions. So for data mining small problems with 8, there's 28 predictors. For larger data minings, we would have 4,950 predictors. Is this categorical variables? Interactions between variables, good. So when we want to figure out, when there are k predictors, there are k times k minus 2 possible interactions that being concluded. So what do you learn from this right here? When you get to bigger problems, it's going to be much harder to include interactions. That's the whole point of this bottom part. I wish it was in a box, and we said, for bigger problems in data mining, including interactions might not be feasible. So the goal here is, in a small problem, you try out a lot more with your variables. And also, luckily, your model is going to make sure you don't overfit your model. It's going to make sure you don't throw too many variables in. But the different combinations, the different transformations of the variables, we're going to look at all the different things we can do. Pretty good right here. So here's what interactions look like. Interactions means the way in which X explains Y depends on X2. So repeat with me. 1,000 points first person to put in the chat, and I mean this. The way in which X1 explains Y depends on X2. It is always true the K is interactions. The K is the number of variables. So K, and let me repeat this so I can put in the chat. The way in which X1 explains Y depends on X2. The way in which X1 explains Y depends on X2. That's an interaction, because the way education explains salary depends on experience. The way in which X1 explains Y depends on X2. Madeline and Carly right there, and Adam. We got 3 people, 1,000 points right there. Great job. So on the last slide, the formula you had K. Yep. So K is the number of variables in the model. So when you look at K is the number of X's. So K is the number of X's. Does that make sense right here? And so the way in which X1 explains Y depends on X2. Very important thing we can start here. And then here's your X's, and the amount of X's you have. If there's a lot of X's, you'll have a lot of interactions. If there's only a few X's, right, we see right here, there's only a few X's. This leads to only a few interactions. There's not nearly as many two-way interactions. And when you think about it, it's 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Did I miss one? I think that's right. 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Yeah, that's right? Yes, 28. Yeah. Because it would go through the combinations. It would be variable 8 with 7, 6, 5, 4, 3, 2, 1. Variable 7 with 6, 5, 4, 3, 2, 1. So you can do it as that sort of problem. Did anyone get what I was saying right there? Maybe Nitin got it. Is the way in which you can do all two-way interactions, like this variable with this variable, this variable with this variable, 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 then this variable with this variable. Yeah. So it's all the combinations of two variables that can interact together. And I was literally saying if there's 8 variables, you'd have the 8th variable with the 7, 6, 5, 4, 3, 2, 1, which is 7. Then you'd have the 7th variable with 6, 5, 4, 3, 2, 1. So if that makes sense, how these numbers are being calculated, and then I mathematically did 7 all the way plus 1, 7 plus 6 plus 5 plus 4 plus 3 plus 1. I checked it was 28. So just understanding what's going on here theoretically, but how do we know if there are true interactions? We let the validation pick that for us. So this is what's so cool, is you can throw the interactions in there, and that's what I was doing yesterday. I think we still have those notes open from yesterday. Here, I'm gonna switch screens. I'm gonna click it here. Where's main screen capture? Desktop. So if you look over here, we were doing this yesterday. So how do you know? How do you know if you have interactions? Really good question. We're gonna save this file here because we've done a good bit of work today. R is just not responding ever. I had things unplugged. I was replugging things this morning, and I'm gonna have to replug and reset a bunch of stuff. So let's go here. 474. R, why? Oh my gosh, 474. Okay, let's save this as the 20th. So how do you know if you have interactions? We're gonna go here to data mining. It's eventually gonna start doing its thing, data mining. And what we would do, and we wrote the code yesterday. Where's the code at? It's up here. This right here. You know what's really great is we can search for interactions within this model if we simply, I wonder if it's going to say like rank deficient. Could not find function train. That's fine. Library caret. Oh, and then we're not going to have our data set either. Okay, let's... we're fine. This is it right here, just so you can see. That's how you would check for the interactions right there. So this would now check for interactions in Nisha. Does that make sense that this will now check for the interactions between the variables? You could even do the 3-way interactions, but that's going to be a lot crazier. You could do all the way up to the 9th-way interactions. So you can check for interactions that quickly, and then you'll get the plots telling you where the interactions might be and what interactions, like it'll help you select your model. So checking for which model is the right model, we're going to go by RMSE, and then I'll show it at the end of class right here because ours being so weird. Let's give it a shot. It's very important, like to see the output. Let's go here. I'm gonna have to remake the data sets for this because this is the point of this. Sorry, everything computer's just being so odd today. No. I think this is a really good question. See, like ours literally every time we keep saying like not responding. So we're gonna fit on those. We're not gonna do repeated CV. So now we've got our fit control. Did I load library reg class? Or no. Caret. We need caret. Caret's loaded. Good. Let's load fit control. We got that. And we were using survey 10, right? So we were doing survey 10. Here it is. Here's our, so we have to make a holdout again. So here's where we're making our holdout. So I'm just loading up this part of the data. I know ours said, Brian, it's the weekend. I'm not responding to you. Not going to do it. Not going to happen. Come on, you got this. You can think. It said I'm overworked. Too much work. And so there's that. Lots of good notes in here. Okay, so I'm going to not put this to a crazy thing right here. Yesterday I was doing a really fine sort of regression. Hopefully this it's working. Good. This is the real deal right here. So now, there we go. That's got it. It ran, didn't crash. Now we're going to plot the GLMNet grid. I wish I could see the one we got yesterday. Please show me there we go. Whoa, cool. This is when we predict somebody's height. We would be off by about, we can look at how it does right here. The best model is an alpha of 1 with a lambda of 0.25. So the alpha of 1 and the lambda of 0.25, it's right in here. So it's an alpha of 1, which controls the lasso versus ridge mix. And then the lambda is the regularization penalty. More on that probably on Monday. And let's go here to see how our model's doing. I think we changed all this. And, oh, we computed that last time by hand. No, that's something different. We are not off by 93. We're off by 2.75. And this is, I think, actually how the model is doing on the holdout. The model looks to be doing really great on the holdout. Oh, I limited the output. Okay, it's not on the holdout yet. Yeah, okay, here we go. This is how the model does, our model right here does, and then this is how the model does on the holdout. Sorry, I changed output yesterday. That is not accurate. Our model can't have that high. We're predicting weight. Are we predicting... We're predicting height. I might have switched the model yesterday. There we go. That's better. Whoa! Wow. Okay, I want you to look at this output because this is kind of cool. We got one of those rare scenarios. Here is the validation, and then here is how our model does on the holdout. What do you notice? We're predicting people's heights. And how does our model do on new data? You also see it show up here. Here's the validation. We don't use R squared, but I mean you can look at it. We won't do the activity day. We'll do it on Monday. And do I have the assignment due Monday? We'll do a lot of activity Monday. And this kind of counts as activity a little bit. And this code is posted, remember, for you to take a look at and work with. So we will do activity on Monday. Monday's going to be a big activity day. What do you notice about this to here? What do you notice? This is key. You should notice this immediately. This is like the thing we have to see immediately when we look at this. And it's a good thing. Someone's going to think it's a bad thing for a moment. They're kind of close. I think we won't do Analytics Lab 5 today. We will do it on Monday. Do a time. We definitely don't have time for it today. The RMSE from the validation to the holdout does what? The RMSE, and if I have it posted for today, I'll move it. So sorry if I have it posted today. The RMSE for the validation goes down. It decreases. It does better on new data than it did on its own. And I'm predicting people's heights, and I'm typically off by about 2.75 inches. Now, that might be pretty good. So this model right here that predicts people's heights is typically off by about 2.7. And if you want to switch back to using the non model with the squared terms in it, the interactions, you could make your model here, and we could see how this model does. And this model right here does about the same. It was 2.75 before and 2.52, and maybe it's picking a very similar model, but 2.75, 2 points, and maybe is it doing, it's a different model. But you know what's funny is 2.527 and actually 2.75, that's the square, and 2.752. It actually does better without the interaction terms. So without the interaction terms, it actually does a better job of finding the model. That's the way it goes sometimes. Crazy world of model searching, and that's why we make a bunch of different models, but they're all within one standard error if we look at them. And I do want to point out in this output, you do get the RMSE standard error. So here's the RMSE standard deviation, excuse me. And look at this. does everyone see here, if you want to find any model that is similar to this, you would take this and add to it 1 standard deviation. You would take to it and add to it 1 standard deviation. And by adding 1 standard deviation, you're also adding 1 uncertainty. So any model that is within this would be a similar model. That is a key thing you should know instantaneously, which I'm pretty sure is on our next assignment, that when you have a model like this right here, you would see any model within 1 standard deviation has the same predictive analytics power, or like we can't say they're that different. So it's every model within 1 standard deviation. That's the 1 standard deviation rule right there. Let's hop back. Okay. So interactions allow us to look at how one variable explaining why might be impacted by another variable. If you notice in this graphic right here, people with what values of education would actually have experience negatively impact them. People with very high what education would actually have experience negatively impact them. You're welcome, Anisha. Really good question and a little good. We will do activity for the majority of Monday, so stay tuned. Monday is going to be probably, I might do 2 activities on Monday. Would you guys like that if Monday was a purely activity day? And I think if we have anything due this weekend, I'll put it due on Monday. If we have anything due this weekend, I'll make sure it's due on Monday. People with large education have education negatively impact them. So we'll do like all activity on Monday. We'll focus all in on code on Monday. And I think that's going to be a good plan right there. And I'm trying to think of anything to do this weekend. So we have something to do this weekend. I'll move it to Monday and I'll shift dates a little bit. And then we'll do all activity Monday to focus in on what's the code doing. And people can ask some questions. And we'll probably do 2 activities on Monday. So make sure to be here Monday. So that's a big announcement right here in class. It's due tomorrow. Which one is 6 is not? Is 6 Market Basket? Is 6 Market Basket? I just can't think. Is 6 Market Basket? Associations. Yeah, it's Market Basket Associations, right? There won't be a lab due tonight. There won't be a lab if I put it due tonight. With Market Baskets. See, I wish I could do. I'm trying to think, should I just do Market Basket for the last bit of class right now? Because that one I want to be due. If we need a vote. We need a vote. Here's Brian's suggestion. Brian, I feel like this is a bad idea. I'm worried. Just remember, we need a vote. We're going to vote on something. I can be outvoted. I would say we should keep the due date as is, but I can adjust the due dates so that we do the activity on Monday for Market Basket. And I did some of the code yesterday. So if you look at, Jordan was here yesterday after class, and we did a lot of the code for it yesterday after class. As is, here we'll see what people vote. If it's kind of close, I might outweigh. When is homework 6 is due tomorrow. So this will there will be more. Let's go to polls. Okay. So what will happen is, let me make it very clear. Market Basket due date. Okay, so here's the vote. You can vote for either, don't vote yet. If you vote for Saturday, which will be S, it'll be moved, it'll stay on Saturday, or we have Monday, but this will shift the other dates. Everything will still be due, which then I'll get emails from people being like, there's no way I can do all these, but I'll go with whatever the majority opinion is. But there will still be, because we do everything as a class. So we vote as a class, and if you're here, you get the vote on it. So it'll, if we change the Saturday homework, I won't put 2 due on Monday. I won't make 2 due on Monday. I'll move the Monday. It could be due on Tuesday. I won't ever put 2 due on the same night. So I'll shift them, but it'll kind of it'll bulk up more areas. Does that make sense? I'll kind of distribute across the timeline. So I won't put, I won't ever put 2 due on one night, because then people won't do that. I know how I've taught long enough to know if you have 2 assignments due, it's not happening. It's just a bad idea. So it looks like we have a winner, and I will do some activity on Monday, which is like the benefit. I'll focus in on activity on Monday, and we're doing fine on time. It's just realize that please be looking at the market basket this weekend. Please be looking at the next homework this weekend. Here's how, and it looks like it is winning out. Monday's winning out by a good majority. You guys get the votes, and I said, I think it's fair enough. I get 1 vote, so I get to overturn it. But be voting right here, unless there's a flood of S at the last second. It'll be changed. So can I change it right now? Let me go in and change this. If you want, make sure to do it. Someone send, who's going to be my email reminder person? I need an email reminder person who's going to email me and say, Brian, change those due dates. Who's going to be my email reminder person? Who's got my email reminder? Let me look at the due dates real quick. So 16th, the 20th is when, association rules 20th. Okay, we've got a 3-day span here, 3 days. Oh yeah, we're good. We're fine. Concepts in predictive analytics, vanilla and regularized logistic. Yeah, we're fine. Got tons of time. Okay, so first person was Kelsey. Kelsey, you got 100 points right there. Kelsey, on top of your extra credit email today, in your extra credit email, and Caroline, you're the double reminder. Caroline, you say, Brian, did you change those due dates? Did you change this? I agree. Vader knows right. Yep. We go by fair in this class. We close the poll. We complete the poll. That's the way we do it. We vote on these things. So thank you everyone for voting. As I say, I listened to everyone, and had it been, I would get 1 vote. I get my 1 vote. I'm 1 vote. I'm 1 say. So you guys can be like, let's vote. Let's vote here. Should everyone get A's? Let's vote on this. Should everyone get A's? Yes or no? Let's start the poll. Okay, wait, let's close the poll. Okay, wait. Oh, so no one voted. No one voted. Cancel the poll. No one voted, so I get to vote. Well, we'll do grades based on we'll poll is over 5, right? Yeah. Adam's like super quick on that one. It's Friday. It's fun day. People are voting yes. Sorry. Poll's been canceled. Streamlabs canceled that poll. It didn't like it. I just clicked on the only one I had open for a yes or no. Okay, you guys having some fun? I'm having some fun. Here, let's do a little more talking here. Remember, Monday we will do labs, so make sure you're here. We'll do 2 labs on Monday. Very important day. It should help a lot with the assignment. I'll probably handle some assignment questions. So I think that'll be a really good utilization of Monday. So if you're worried about the bulk of assignments that are about to hit us, this was the big test week. Next week's going to be a big assignment week. If you're really worried, be here bright and early on Monday. I mean, not too bright and early. I mean, I'll show up for 3:20 if you want. We'll be talking similar concepts in there. But show up on Monday, and we will get a lot of your work done. I'll take homework questions too in there. Like, we'll do lab, and we'll do like homework and lab at the same time. So we'll focus in on that. So Monday, show up. We'll get lots of work done. Let's do this. When predicting salary, yada, 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 showing the interaction. There we go. Transforming. This one right here, we can do these slides a little bit quickly, because the hardest thing about transforming Y and X is that how do you transform it? Thank you, and thank you, Andrew, right there. You guys are awesome. No, you're breathtaking. Some Keanu Reeves right there. Best, greatest man in the world. It was Nicolas Cage, and then Keanu Reeves turned out to be awesome. So this is the hardest part. We mentioned this earlier, that figuring out, thank you guys in the chat right there, figuring out the best like interactions between, or not just interactions. Well, yeah, you have to figure out the interactions. Transformations are harder because, I mean, you could write a function that, like the find transformations function. You can find transformations, but it's like so impossible. It's so hard. So when we do this, we often want our X to be pretty normal. We want our Y to be normal. So the model has difficulty predicting things that are outliers because it's going to try to fit to that. So a lot of times we will transform our Y variable. So we transform our Y to make it more normal, to make it predict better, because when there's outliers, the model will often fit to outliers, causing these points to have undue influence on our model. So why do we transform variables? To achieve normality. And if we transform things, we have to transform them back. So here's where we transform it, because the totals movies make is very skewed, and we don't want to deal with this. The first step of making a predictive model for Y is to look for the distribution of Y and to see if we need a transformation. Because if we try to predict on the movie totals that are extremely skewed, and so I should have done that. Well, I was predicting height, I think, or weight, one of the two. Those aren't that skewed. They're pretty normal. So I should have looked at my distribution to see if I can accurately predict this one. If it's heavily skewed, which this one is, log transformation is usually good. You can look at the find transformations output though. It's really good. Outliers have huge impact on our model. So we generally work better with symmetric models. Nearest neighbors and support vector machines tend to work better with symmetric predictors also. So the X's, though making transformations somewhat changes the notion of similarity of inner products. Not that big of a deal. Tree-based models introduces rules between two unique variables predictors. So symmetry and skew is not as relevant, especially because it's going to make a cutoff point. And this is something so funny. When I was talking to Dr. Petrie so long ago, like 5 or 6 years ago, I was transforming my variables in my tree models. And he's like, why are you doing this? And I was like, because we're supposed to try transformations. And he's like, you're just stretching it. In a tree-based model, you find a point of division. So it doesn't matter where you stretch it. You're going to have the same point of division in like the tree-based model that does like greater than this, less than this value. So it's still going to have the same arbitrary cutoff no matter where you stretch your number line. Now, when you stretch these numbers, once again, these numbers right here are not going to have their order changed. We're not mixing up the orders of these by transforming them. We're kind of bringing them in together. We're crushing them in together. We might stretch something with a transformation or crush it in with a transformation. So you would still have, if you had a cutoff point like here, that cutoff point might still be here in this data. So you're not going to change where the cutoff point would be. Now, technically, we could figure out right here, 100. Yeah, and then this would be this over here. So that would be that point right there. No, that's 102. What am I doing? I don't know my log scale anymore. It's like it didn't look accurate for the amount of data. And then that would be right here. So it's still the same arbitrary cutoff. The same amount of data would be above it. It's just looking different. Like this amount of data right here should be the same amount of data right here. And it looks like it's more just because there's more bins. So it's a different scale to the visualization you're looking at. But it's still the same cutoff with the same amount of data. So the tree-based model transformations are not that big of a deal. So once again, the thing we should know is that linear and logistic, we really need, both linear and logistic are going to need transformations. Things that we will talk about coming up here, nearest neighbor and support vector machine, both of those right here are going to need our X's especially transformed on the predictors. And we can transform predictors in our model too for the linear and logistic. Tree-based model, it doesn't really do anything. It's a waste of predictive power. Not that big of a deal. Now we're hopping into some linear regression right here. Time to talk about pros and cons. Once again, linear regression is one of the easiest things we'll ever do. Making predictions is easy. You just plug in a number into an equation, you solve through, boom, 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 got it. If the assumptions hold up, like if it's linear, if it has equal spread, if it has all this stuff, it's a good reflection of reality. Yeah, it is really the only statistical model we will consider, meaning its theoretical properties are known and we can talk about accuracy. It's such a good statistical model. Everyone uses it. And we should get to some cons here in a moment, the bad things. No cons? Cons, here we are. Form of model is chosen fundamentally wrong, because what we're saying is that there's a linear relationship between the variables and all models are wrong. And once again, coefficients of the model are chosen based on bias, and we are not going to take into account regularization. We will do that probably starting Tuesday because we're going to do Monday activities. So we need to make sure we select the coefficients of the model based on some sort of regularization parameter. Interactions can be difficult to find and consider because there's a whole ton of them. When you include predictors into models, there can be tons of combinations. So with just 30 predictors, you'd have 1 billion combinations of variables that could be used to predict. If no interactions are considered, if there are interactions, there's way more. So how to choose what exactly is the model, what do we do, what transformations do we do? It's just really hard to understand, like, what is the relationship between your y and your x's? So what do you do? So despite all of these issues, it's still just a super simple model that's easy to interpret. This is why, has anyone seen linear regression outside of business analytics? Let's see some yeses in the chat or nos. Yes or no, have you seen linear models like someone doing a regression outside of business analytics? We'll see. Yes, it's everywhere. It's like the model of choice. It's the most common model there is. It's just a line. It's a line with more variables. It's out there everywhere. 100 points. Thank you everyone for being here and participating. Marketing, yeah. It's why we're doing it in data mining also, because everyone uses it. You have to know it really well, and you have to know it has assumptions that we're assuming there's a linear relationship between your x's and your y's. You might have to look for transformations. You might have to look for interactions. You can include categorical variables, which blows people's minds. They're like, wait a minute, how can you include a categorical variable? And it's because we're treating it like it's an indicator variable where we treat it as a 1 or a 0. So the only value this takes on right here is either 1 if it's Saturday and 0 if it's not. So this variable right here becomes basically a quantitative variable. It is the day Saturday, but we treat it as an indicator. If it's Saturday, this would become 1. If it's not Saturday, it becomes 0. Just like bill becomes a certain amount. Like, what was the bill? We just plug in the bill amount. This Saturday is going to become an indicator telling us if it is Saturday. So technically, it is still QQ straight enough, no outliers, because we're treating the categorical variable or the factor, the level of the factor, as an indicator with only values of 1s and 0s. So we are tricking it into being a quantitative variable, which is just like, wait, what? It's still QQ straight enough, no outliers? Yep, it is. So we see all this right here. We're good. We're good. Oh, man. Oh, man. Regularization is so fun. Let's talk about it just for a moment. What is the problem with regularization? I'm going to do a speed run of this right here, right now. I'm just going to keep it here on the screen. No timer on the screen. Check it out. Pay close attention for 5 minutes, and I'm going to try to teach you regularization. We will come back to this, but pay attention for the last 5 minutes here. This is key. The more times you hear this, the more times the better you'll understand it. When we just do regular old regression, all we're doing is selecting on minimizing the bias. This is showing how it's done and everything right here with all the code. But all we are doing is trying to minimize the bias. That is the only thing we are doing in just regular old regression. Just normal old, regular old regression just tries to get the smallest error. And we pick based on which error is the smallest loss function. This is the lost variable right here, what we're trying to find. Whenever it's the smallest, due to the RMSE, you notice right here, the sum of the squared error, well, that's the SSE, excuse me, which is basically RMSE, but calculated differently. It's not the same, but uses the same numbers. But now we're changing the name of the game. Instead of just caring about this, instead of just caring about the errors, this is the fundamental wrong way, which was the con, the bad part. When it said we fundamentally picked these wrong, this is what it was referring to. Because by only caring about the bias, 1,000 points first person, what are we not caring about by only caring about the bias? By not caring about the bias, by only caring about the bias, what are we not caring about? By only caring about the bias, what are we not caring about? If we, boom, oh no, variance, Jordan right there. Jordan got it. Yes, variance. We're not caring about the variance. The variance, I'm being super nice. It's Friday. If you answered it, you're at 1,000. It's not on top of it. You're at 1,000. I really appreciate it. If you answered that and you're here to the end paying attention, you got it. Because this is the problem that this fixes. Because now, what we're going to optimize on is not just the bias, but also the variance. We're not optimizing on only the bias. We're optimizing on also the variance. But look what we can do with this equation. If I just set this equal to 0 right here, what would this do to this if I set that lambda equal to 0? If I set that lambda equal to 0, then what will that do to the variance component of how much I'm trying to weight it? The weight of the variance component will be 0. So guess what? If you do that, you're just doing regular old regression again. Because now you're just doing regular old regression. So if you remember from my code from today, let's hop back here to the screen, the main screen. We'll pull up R while that's doing that. You gonna do it? Desktop? Go desktop here. So if you look at this right here with this code, this lambda right here, this lambda, if I have lambda equal to 0, then I'm not doing a regularization on it, which regularization is how much we're accounting for the variance component. And so you see lambda can take on different values, and we see that over here in the output, that the regularization penalty can be very small or very big. And look, if we didn't include a regularization penalty, we would have gotten a worse model. And then what is the right amount of regularization penalty? How will we do this? By tuning the parameters. So if you notice here, I can choose, this is literally the value of lambda. I can make lambda very small, or I can make lambda very big over here. So lambda can be very small, which will not penalize myself, or lambda can be very big. We can switch between them right there. And I've got like 1 minute left. 1 minute, we're done. So new everyone. Yes, we are. So with this in mind right here, we have two ways of doing this, and this is the easy part. You have either ridge, which penalizes you based on the square of the coefficients. So what is ridge going to try to do these coefficients? Give me 1 minute more. What is ridge going to try to do these coefficients? It's going to try to make the coefficients vary what? If this is going to be, we want this whole thing to be small. So ridge is going to try to select coefficients that are very what? It's going to try to make your coefficients very what when you select them for the model? It's going to try to make your coefficients very, 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 very what? Small. Does that make sense mathematically here? Because you want this to be small, and this is how much you're penalizing yourself based on the size of the coefficients. So this is the variance component. That's the variance component. That's the weight of the variance component. This is the variance component right here. This is the weight of the variance component. And that's ridge. And guess what? This is lasso. Lasso, here's your variance component. Here's the weight of the variance component. This is the bias. And this is what we're optimizing on. So now you could set this equal to 0 and not have any account for your variance component right here. So that's the weight of the variance component, and this is the variance, like due to the coefficients that we're taking. Once again, in lasso, we're just doing absolute value. It's kind of like RMSE versus MAE, because you can either square the coefficients, or you could take the absolute value and try to minimize how much you're taking. And the only other thing we have to know is elastic net regression, which elastic net takes some ridge and some lasso, and there's your variance component, and there's the weight of it. So what is the goal of regularized regression? In regularized regression, we're also optimizing on how much information we take. And sorry, I went a tiny bit over today. It's Friday. Thank you guys so much. But who thinks they kind of get this? We'll be reviewing it more. But who's like, okay, the difference going from regular old regression, which we sometimes call vanilla regression, to regularized regression is now we're not just trying to get the model that fits the best. We're trying to optimize on how much information we take to minimize the amount of information we take so we do not overfit. And let me repeat that statement. So if you want to write that down, that's key. The goal in regularized regression is not only to optimize how well the model predicts, which is the bias, but to get a model that takes as minimum amount of information as possible, which is going to be the variance component. So we're going to penalize ourselves for the information we are taking, and we'll look over different values of the penalties. And that's how we'll do our tuning grid to see what is the right amount to penalize ourselves. That's literally what you see over here in R, is we're trying to see what is the right amount of regularization penalty and what is the right amount to mix these. So we are trying to tune the alpha. Here's where the alpha is being tuned. If you notice, there's an alpha in here. So we will try to figure out what is the right value for the alpha, which it's just one alpha, but it's here twice because it'll choose how much ridge or how much lasso we take. And then the other thing is how much do we penalize ourselves? Here's where we chose our values of alpha, going from all the way from all lasso, I believe, to all ridge. And then right here, you see the regularization where we have no penalty for the terms to a larger penalty. And we chose somewhere in here. This is our optimal model. Who thinks they kind of get this? Anybody? Or like on a scale of 0 to 10, how much do you get this? 0 being like, I have no idea what the heck's going on. 10 to being like, I understand this. I know it perfectly. Had you ever done this before, Anisha? Have you seen regularized regression, elastic net, lasso ridge? 8? Awesome. 5? 90%? Good. We'll be reviewing this. I did it really quickly. 5 minutes. Good. I like that people are like, I kind of get it. Kind of, yeah. The point of regularized regression is to consider the variance component. The point of regularized regression is to consider the variance component optimized thread. How to find the best point in the graphic? It'll show you. Here, wait. Let me go to main screen. All you have to do to find the best point. Where's my main screen? Everything's being crazy today. Desktop. So if you're like, where's that best point in the graphic? All you have to do is run the following code if R wants to do its thing. See, look, not responding. Stop not responding, R. So to find the best point in this graphic, you just run the following code right here. I'll show you which one screen. Here it is. It's this one right here. So you go to your GLM net and you go to the results and you go to the best tuned. So it'll literally, it knows via this right here, the best tune, it saves into there the best tune. And there's the row with the best tune. So we're going inside the GLM net results. So if you go to GLM net results, you can look at every single model you created. So we're going to make a ton of models right here. It looks like I've got a couple hundred models maybe. And yeah, I've got 200 models. And so I made 200 different models. And from these 200 models, oh wait, there we go. So here's my 200 models. And from the 200 models I made, it's going to figure out the right combination of lambda and alpha that optimize the RMSE. And it looks like you can see the different things. You can see the RMSE getting lower right here. What's that? That's my RMSE standard deviation. I was like, that's weird. 2.76. And a lot of these models look very similar. But there we go. And I might not have even seen the best one on the screen. But does that make sense, Jinning, right here, that this graphic right over here is the visualization of the RMSEs. Error, hey, what's up, Error? No one block Error. Error is good. I know Error. But I decided to stop by. Hey, so good to see you, Error. Look at this beautiful graphic we have. It's our values right here. So good to see you, Error. I know you were coding, right? I think you were coding like some bots and stuff like that for maybe Minecraft. So good to see you, Error. I remember joined in. Yeah, congrats, Error. Congrats on all that. You got your website up? Yeah, that's awesome. Congrats, man. Congrats. Great job. Keep working, keep coding. You can look at all the code we have on our screen right now. We've been coding away. This is, we're doing some data mining right now. So we've got all this code right here. Tons of stuff, hundreds of lines of code. We didn't write all this today, obviously. Hosted on your own VP. Whew, great job. And they'll tell you in the chat right here that if you're learning how to code throughout school, one more question, why this alpha is best? I don't get it. Yeah, okay, so there is no always best alpha. So here's the different levels of alpha, which is how much. Okay, so what this does right here is we asked with our tuning grid. I'll show you the tuning grid again. So alpha equals computers being so crazy today. We asked with our tuning grid to, if it ever loads, to tune different values of alpha. So what I could do, watch this, Jinning, is I'll go here and I'll change it to 0.2. So now when I run this, it's going to go from an alpha of 0 to 0.2 to 0.4 to 0.6 to 0.8 to 1. We could do this and we'll only do 3 values of alpha. This will be much easier to compute. And now my graphic, do you see this right here? I only tested 3 different values of alpha. Does that make sense, Jinning? What happened here is I only have 3 different values of alpha. This, I believe, is all lasso. This is 50-50 lasso ridge. This is 100% ridge. Does that make sense right here? We've got all lasso, 50-50 lasso ridge, 100% ridge. And hopefully I'm remembering which one is lasso, which one is ridge. I could go look. And you know what? Let's go look at the thing. Which one is which? Okay, the one is all, let me just show you. If you were to put in here 1, it would be all lasso. 1 is all lasso. Because with 1 right here, with alpha being 1, you would have only the lasso component. So it's a ratio of how much you're taking. You're like, either I'm going to take all lasso, all ridge, or somewhere between. Does that make sense, Jordan? Like the alpha is, yep, there you go. And I reversed. Sorry, I reversed it earlier. It just means how much you're mixing them. It's like, to me, I'm just like, okay, we're just going to mix the things together. And I'm like, well, let's just see right here. So theoretically, I guess I should know alpha of 1 is equal to all lasso, but I can look at I can be like, I can check. If I ever wanted to check, I could just be like, which one is it? Is it all ridge or all lasso? But I know what it does. More importantly is not knowing that an alpha of 1, you could put this on your cheat sheet because I could technically ask it during the test because I can put this on my cheat sheet. It's more important to know that it's how much you're mixing them. So you can mix them 50-50. It's like, putting some lemonade and iced tea together. You could do all lemonade, you could do all iced tea, or you could do your 50-50 mix, which it looks like. I might need to vanish right here. Where's my new video? New video. Bop. There we go. So it looks like the best answer is somewhere it's either this one or this one, but I'm guessing it's the green one. So we can easily find out the best tune with this. It's an alpha equal to 1 with an lambda equal to that right there. Does that make sense? Like when you look, it literally will tell you it, and then you can have it evaluate the model for you right here. and it'll give you the results on it right here because the alpha 1 with the lambda. And so you can see this is the best. Now, it gets much more complicated if you make this grid finer. When you make the grid really fine right here and you do this, you're going to get a really interesting, you see it's taking more time to run now. So now it did a much more finer result. And now when we look at our best tune, it's an alpha of 0.7 with a lambda of 1.99 right there. And probably the differences we saw from the first models were due to the validation portion being different. So the goal is the lowest, for this one, the goal is the lowest RMSE. Yep, and then here we go right here with this RMSE, and then we will see how it does on the holdout. Oh my gosh, what did I do? I literally hit like control something and ran every code. Well, let's just watch it run right here. Can I not even stop it? Oh, selection. Oh no, what have I done? Oh, error, that's awesome. Yeah. You've seen a bunch of model building. Yeah. You've seen a bunch of model building, all this great stuff. There we go. I exited out of this right here. Yeah, no, this is, and you look, we've got a model right here with a kind of putting a line through it. And you see all of this is very important because, especially with current world event, you know, we try to make predictive models for what's going on. And we know, we say it all the time, one of our favorite sayings in this class is all models are wrong. Let's just type in here wrong. All models are wrong. Some are useful. You're never going to get the true models. And I'm usually at your streams. I just went on a hiatus because of school and stuff. Well, congrats. Yeah, keep working hard at school. And tell them, be like, hey, I'm watching, some classes on analytics. You're always free to hop in here. So no one block error or anything like that. I can make sure that doesn't happen. But you're always free to watch and learn with education. Hey, you're welcome, Janine. Great to have you. And everyone have a great weekend. But yeah, we want to help out. We want you to learn. And the more you learn about analytics and everything, BAS 474 question for homework 1 on 6. For H1 on 6, do we need to just create a subset with our favorite artists, including in the left-hand side, right-hand side, report the, yeah, let's look at that. Let's pull up that homework and hopefully R needs to stop being crazy. Look, I was going to say not responding. I'm going to look into this after class and be like, what is going on? What is going on with the world today? That's their assignment. Associations, homework 6, but not 7. 1H. So we need to go. So this is kind of, you'll like this error. We've got playlists of artists right here. So we're looking at what music people listen to. So remake the rules. And so the way this works, so especially for any 474s listening in, we have people's playlists. Like if you went to someone's Spotify and you took their Spotify playlist and you're like, okay, what do they listen to? We're going to see the associations between people and what they listen to. Like maybe someone who listens to Counting Crows would also listen to Green Day. Someone who listens to, let's say, I can't even think of any other artists. I don't know. Let's say BTS listens to Block B, some K-pop right there. So we'd have all these different things right here. So we're looking at the associations between different bands, and we have people like Ashley Tisdale, Black Eyed Peas, Jennifer Lopez, Lady Gaga, Madonna, all these guys. I play for, awesome. Yeah, the GitHub education, great error. You are on track. You are learning at a very good rate right now. You're on track. It's all about coding. It's all about programming. Keep up your education. Keep learning. And the biggest thing I tell my students, it's not about like grades. I mean, congratulations on that. It's not, grades are important, but if you want to get a job at Silicon Valley one day, if you want to get a job working for a tech company, they're going to want to see what you've done. They're going to want to see the code you've made. They're going to want to see how well you can do if they were to say like, here, code this for us, or debug this code, or can you explain this? Yeah. I don't even know what Microsoft Azure is. I don't even know what that is. So they're going to want to see what you can do. So I always tell my students, like, you have to learn skills and you have to look for them yourself. Computer's just being crazy today. And so we want to learn what the a priori learning method is. So here's what we're going to do. We're going to take our code we've already written. Oh yeah, VPS hosting. Yes. And here's our code we wrote yesterday. Is this the updated one? We fixed this. I need to resend this. Okay, so here we are. So let's go ahead and, so Jordan, this is 1H, right? Let me find it this way. 1H. Okay, here it is. Remake the rules mine so that the minimum support is this. So we're going to drop in our code from yesterday. We're going to grab the min support. Boom, got it right there. They have to apply to at least 30 listeners and a minimum confidence of this. So we're going to take the confidence. So the support right here, what the support is, computer's just being so crazy. We're going to try to fix it later today. The support right here is how many people have to have these bands in their playlist. That's the way to describe it to someone. It's like 30 out of the 1,821 people have to have these bands in their playlist. Whatever the bands are in the rule, like if it's Counting Crows Green Day, 30 people out of the 1,821 playlists have to have those bands in the playlist for us to consider them. The confidence means how confident we are given somebody likes Green Day that they'll like Counting Crows. So the confidence is we need to have at least 25% confidence if the rule is going to be written. If we're going to write a rule like how does somebody listening to Green Day impact them listening to Counting Crows, it would need to have at least a 25% confidence. Do we have anything else? Don't remove rules in this case. Okay, don't remove them. Got it. So I may or may not be running a 120 gigabyte of RAM. I know, right? That's, you know your stuff, Error. Think of an artist or artists that you particularly liked back in 2011. So if you see any of the rules involved, them on the left-hand side, do mind the spelling, yeah. Okay. So I think we should have everything right here. Are we considering lengths of any rules? We're going to figure out what's going on. I've got some people helping me out this a little bit later, figure out what's going on. And we don't have, we don't have rules loaded up. So I'm loading everything above because I don't have the libraries loaded up right now. Basically, I don't have the functions and everything error. So I'm getting another error. We don't have music. We need to go to session, set working directory, choose directory. We need to go here to the downloads, and we need to go ahead and open that. Now we should have everything we need. I'm going to reload everything above. There's the music being read in. Right there, we're loading in music, which takes a moment. It's a big transaction data frame. And ours just going to be weird, as per usual. And now we've got it. So now this will run because we're going to create rules using the a priori learning method where we're going to have certain parameters the rules must follow. So the first argument here is what do you want to create your rules from? And the second argument here is what conditions are you going to make for these rules? Well, my rules have to have at least 30 people liking the artist, and my confidence in the rule has to be at least 25%, and the verbose equals false just limits output. If you do verbose equals true, so that's a control for this function as it runs. If I did verbose equals true, it would print a bunch of stuff to the screen. I don't want to see that stuff. I just want the rules to be created, and now the rules are being created in the background. Once again, if verbose was equal to true, it'd be verbose and just start printing things to the screen. But we've now created a bunch of rules right here. So when we look at these rules, we've created 3.5 million rules. 3.5. Good seeing you, Error. Exactly. Have some fun on CSGO right there. A little Counter-Strike, global, I don't know what the O stands for in it, but some CSGO. So have some fun on some CSGO. Enjoy. We're going to inspect these rules right here, and my computer's just going to do its thing. But good to see you, Era. Global Offensive, that's what it is. I never played CSGO. I think I'd like CSGO. I never played it. I liked Transformers War for Cybertron. Man, that game, I play the game all the time. So if you look at the different artists we have here, we've created different rules, how people, and we could sort these rules. Oh, there's like a no artist thing. Ooh, that's interesting. Maybe that's a new thing, or maybe I just never noticed that. Does anyone have a band they like? Who has a band they like? Because now we have to go and find these bands. So think of an artist that you particularly liked back in 2011. Don't use any of the ones already used, and see if any rules involve them on the left hand or the right hand side. Do mind the spelling. And so we want to find them on the left-hand or right-hand side. So what we want to do now is we want to subset these rules. So you want to go to subset of the rules, left-hand side, and %in%. Now what you can do is, we figured this out yesterday, is you can go %in %, and do like Ben folds. Now this will subset, it should say subset of a certain amount of rules. Is it going to just say it? Subset of 0 rules. No. %in %Ben folds. Subset of 0 amount of rules. Is he not in any of the rules? He might not be. Maybe he's in the right-hand side. Here we'll cheat and we'll grab Miley Cyrus. There we go. Depeche Mode. So they're on the right-hand side, so we should see them. Let's see. Oh, so Ben, yeah. Well, we did fine. Ben Folds was not in there. Sorry, Ben Folds. We don't have rules for you. Depeche Mode is there, so you want to pick something like Green Day. You want to go to a band that's more popular than Ben Folds. 40 rules for Green Day. So does this make sense right here? It says to pick... I'm going to reset everything today. Think of an artist that picked a leg back in 2011 and see if any of the rules involved on the left-hand or right-hand side. Do mind the spelling. So now, print to the screen 5 of the rules. If they exist, they might not. So try to pick something that exists, because it's no fun if you don't. But make sure your code's correct. So I could pick Ben Folds and show he doesn't exist in these rules. But here's where I want to put in a second condition right here. I want to go to or left-hand side %in% Green Day. Now, this should make the rules increase. So if you notice right here, I'm saying, is Green Day on the right-hand side or the left-hand side? Make sure to read. The right-hand side of the rule has Green Day in it, or the left-hand side. What did I do? Error in %% Green Day. Table contains an unknown. Oh, ha ha ha. That's what happens when you make a typo. One typo, everything breaks. That's what we don't like to see. We can go here to sub, and we've now made a subset. I'm supposed to print to the screen the rules. You're welcome, Jordan. Excellent job. I'm going to do something better here. I'm going to go to sort, and I'm going to sort my sub, and this is how I'm going to sort it. So I think we should be able to go to, I always forget how to do this one. And let me open it up right here. I always forget how to sort the rules. That is one thing that just jumps out of my mind. Good thing we got the notes. So let's go to the sort on it. Sort rules, and then by. It's just by. Because it's that argument. Sort rules by equals confidence. I'll figure out what's going on. I just think something's stepping on something in the background. By confidence, and that should be good. We don't want to show all the rules. So we have to go inside of here, and after this, we have to go to rules 1 through 10. That should work. Yes. There we go. And you know what? No, that's a bummer. Oh, it's fine. So this is people who really like Katy Perry, which, you know what I want to do? I want this. Don't do this for yours. Now the left-hand side should only have Green Day. Wait. Oh, that's the right-hand side. Oh, so there. The left-hand side can have that, and then I only want Green Day on the right-hand side of the rule. Will that do it? Will that do what I want? There we go. So Green Day, there we go, there we go. I like this. I like these rules now. So what I did was I changed, because we were looking at OIN yesterday. OIN is only in. And so just look at the small differences between my code. The right-hand side right here can have Green Day. So the right-hand side, I could have used OIN, probably would have been fine. But OIN right here means on the left-hand side, they can only have Green Day. They can have Green Day on the right-hand side or only Green Day on the left-hand side. We're going to get the same rules if we also did an OIN here. But this is why Green Day appears here, and it's the only thing. So you notice we got a rule of Green Day and Paramore, and if somebody listens to Green Day, the probability to listen to Paramore is 46%, which is a 2.314% increase. So I'm going to sort it by the lift now. And let's look at these lifts. If someone listens to Blink-182 and Paramore, the probability they listen to Green Day is 4.416 times greater. So yeah, I mean, Blink-182 and Paramore, that's pretty much like pure Green Day. Offspring and Green Day. I mean, all these, if anyone knows Green Day, this all makes sense right here. You could switch to a different band pretty quickly and look at similar rules. Like you could go to Blink-182 and just drop in Blink-182 here, and you could do this. And what's even better, here, watch this. Check this out, Jordan. Jordan, are you still here? Hopefully. Oh, what do you think the blanks are for in the... It must be that it's a blank, because if we go here, and if we go to item frequency, and if we go to music, and if we go to position blank, maybe it means they have... No, it can't be. Is it this? No. Let me do this. Item frequency. This should print all of them. Okay, good. Let's look at the start of it. Da, 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 da. Well, you know what? Much easier way to do this. How many music items are in here? 1459. That can't be the end of it. Omitted that many entries. To do 1,000? Does it print this screen 1,000? Yeah, I don't know what's going on with those blanks. Is it the item frequency of just that artist? Yeah, let me look at the blanks we got in the output again. Let me think about that. Because that did confuse me. I shouldn't have printed so much of the screen. Because do we still have it? Oh, it's going to be so close. Oh no, did I run a whole bunch here that just like ran everything? Yeah, we lost it. What code did I run, Jordan, that gave us the blanks? Oh, it was inspect rules right here, right? Wasn't it? There we go. There we go. Oh, you know what it might be? No, everyone, so it looks to be, yeah, it has a lift of 1. Yeah, so when you look at a lift of 1, so here's the thing, we should get, if the confidence, maybe it gives you, you know what it might be giving you now? Maybe what this code does now, which I'd be shocked by, these might just be the top 3 artists. Maybe the way it works now when you look at this is it gives you, if there's a coverage of 1, and so we talked about coverages at a different time, which Connor told us what coverage was, and he looked it up, and I have yet to memorize it perfectly in my head. But if we go here to item frequency, it might just be what the code does now. It gives you these artists. And we go to item frequency of music, and then we go to the Beatles. The Beatles should have an item frequency of 0.12 right here. They should have this. So let's run it. Yeah. Okay. That's weird that it's doing this. And then Britney Spears is going to have 0.2702. Run! Do it! Don't stop not responding to me. So, so the lift of 1, it looks like they're saying these rules right here are like the left-hand side of the rule is not going to be impacted. Like there's no left-hand side right here. There's no left-hand side. They're not saying someone has nothing. They're just doing there is no left-hand side. Does that make sense? There is no left-hand side. So they're only saying, what's the probability of someone having Lady Gaga? And the probability of someone having Lady Gaga on their playlist would be this right here. And so they're just literally looking at, you know, what's the probability of someone having Lady Gaga? And I think that's new to the code because I don't remember it doing this. It might just report the top 3 artists. It seems to be what it's doing, you know, and these are just 459 people have the Beatles, which does seem important. Like it reports the top 3 item frequencies now, which might be a change because I don't remember it doing this, or maybe I just didn't look specifically enough. And the lift being 1 just means there's no impact. There's no left-hand side, so we're not even considering an impact here. So I don't even think it should put lift. It should put like NA for lift, in my opinion. The lift should be NA. The confidence. Notice what about the confidence and the support right here? Since the lift is 1, the confidence and the supports are what? I mean, they might look different, but they're not. It's just, they're rounding decimals. So the confidence and the support are the same because the lift is 1, and then the coverage. Oh, I should look at what we don't teach coverage in the class, so I just don't know it because it literally when they updated the code, coverage appeared. You could watch last year's lecture, and you wouldn't be seeing coverage in there. But here's something really, really cool we can do. So I was thinking about, you know, like let's say someone just wanted to look for an artist here, like Depeche Mode or whoever. So with this code I've written, be careful here. We'll change it back to what it was. We'll change it back to that. What we're going to do is we're going to have somebody take this code right here. I need to, it got like worse as class went on. So this is, so we go here to fun. Does the screen just blink right there? I don't know what's going on. Okay. So we go to fun, and then we're going to put in artist, and we go here, and we go to create rules. So we're going to do this. We're going to go to code, re-indent lines. There we go. And we're going to go to return. We don't want to return that. That was something we did extra. We're going to go to right here, return this right here. And then this will become artist right here. And this will become artist right here. Create rules. and then we go to create rules for artists, create rules, and then we put in like Ben Folds. And it should create the rules for Ben Folds and return them to the screen out of bounds. So we put in something like the Beatles, and it should create, I think Ben Folds had no rules was the problem. There we go right there. So we've created the rules. Did you have an artist you wanted to see the output for? Jordan right there. Do you want to do like the Who or anybody? So you can literally go here and just enter in the Who now, and then it'll print for you rules for that artist. If you think about the application of this, and this is what I like to point to in our class, is it's all about the application of what we're doing. So that someone could say like, oh, let's look at rules for Led Zeppelin. And you could just punch in Led Zeppelin, use the Beatles, yeah. And so now you should get things like this instantaneously. And I've got mine sorted on confidence. So you could even change what it's sorted by. But if you look at how easy it is to do like, you know, Black Sabbath, and you go right here and you just run that, and then it just finds you the rules. So you could put this into like a web app for someone now, and someone could like find rules and stuff for certain artists. Like if someone likes Black Sabbath and Megadeth, Judas Priest would have a 15.2% times more likely to be liked by them. And it kind of makes sense. Black Sabbath, Megadeth, Judas Priest is going to be like, you can look, Ozzy Osbourne's connected. So you can go right here and check Ozzy Osbourne, and you can see how much more likely people are. Oh, there wasn't enough Ozzy. What we could do is we could limit this to maybe 5, and now we might see Ozzy return results. It says script out of bounds because we didn't make enough rules with Ozzy. So there's the top 5. Script out of bounds was achieved because it tried to create something that was out of the bounds. And yeah, there's the top 5 rules for Ozzy. You can just switch and go Iron Maiden. You just go here. You could even, you know what you could do? Watch this, Jordan. Is we could go here. Yeah, oh man, that'd be so cool. We could call this amount, and watch this. You see how I put amount right here? We go here and we go amount equals 5. So I just set a default so it'll return the top 5 for Iron Maiden, and then I go here and I go to 10, and now I can get the top 10 if there's 10. So as long as there's 10, I can get the top 10. And yeah, it's thinking. It's crashing, but it's thinking. And now it'll return the top 10, or it'll say script out of bounds. There's the top 10. So you can take any band you want, Motorhead, and you can return the top 3. And now we're just getting the top 3 rules. So pretty quick, pretty easy, especially when we change around the function. We'll go to Ben Folds, and we'll do 1 rule. Is there even, I think we saw there wasn't even 1 rule. So yeah, I know that's the point of it, is to like make things easier, to go like AC/DC top 3 rules. So, and they're sorted by lift right now. So now we're getting the top 3 rules for AC/DC sorted by lift. You could change what it's sorted by. You could go, so if you want to change what it's sorted by right here, you would have to go, if it's going to load, we could keep it so it's sorting by lift by default, but you could go right here, grab this, and we're going to call this, we're going to call it Crashy is what we're going to call it. We're going to call this sort by, and then here we're going to go sort by, and call sort by this. If you notice, I'm just making small changes. I'm going to make sure this still runs, which it should, because I just changed it to sort by. But now I'm going to go here, and I'm going to put in confidence. So now it should change, and we should see the confidence sorted by. So now you see it's sorted these rules for AC/DC by the confidence. So I was able to put in a 3rd argument right there. I have the default set to lift, so you don't even have to put this in. You can just run my function right here to find AC/DC, and I think it'll return the top 5 rules sorted by lift. So, you know, you could even put something in like, watch this. We'll put in one last thing. I'm going to put right here cat, and let's go here, paste, and say these are the top, and then what is it? Amount. I want to put paste 0. Paste 0 will put in no spaces, so I can more accurately control my spaces. Will be, these are the top rules sorted by, and then we need to go here, sort by, and then, yeah, for the band, and then artist. Okay, and then we go period. We need a space right here. We won't get the space. And there needs to be a comma here. And then we go backslash and \n. Okay, that should do it. Let's see what it does. Maybe I'll crash it. We won't. We'll find out. So let's see here. Does it show it? Look at that. Oh, look, I missed a space. Do you see where the space I missed is? It needs to be there. Look at this output right here. I missed a space, so we fix it up. And so if you look at this right here, Jordan, you can get, these are the top 5 rules. You know what I also want to do? I want to go here, and before I print this line, I'm just going to do this for nicety. I'm going to make this look a little bit nicer. I'm going to take this line. There's a small little fly in here. I'm going to take this line right here. Oh, is it top 5? There's even a space needed there. These are the top 5. There we go. We're going to put this line right here. Why is it doing that indent? I hate that indent. I'm going to go here once this starts, and I'm only going to print to the screen 2 blank lines. I'm going to print out 2 blank lines to get my output going. And then, let me look at the lines. Yeah, I want it to look like that. Good. And then we'll run this. And then it's going to kind of create a little separation between I run it. But look at that. Look at how much nicer. Would you need to store the operator in the function? Yeah, exactly. Jordan, you're totally right. This only works on the data it's created from. So yeah, you could make your own function that just runs everything. And with this right here, you can do something like this. And you can just change, what you're sorting by. And you can have the person know what it is. And, you can just change it. So if you look at kind of the ease of the functions, and this is kind of one of the goals in the class right here, is if I build this function and make it easier to see and easier to read what's going on, these are the top 7 rules sorted by lift. So you could just change this right here and go to confidence. Ooh, it's gonna like that because that's the order to it, yeah. So it should sort it by confidence right here, and it should say these are the top 7 rules sorted by confidence for the band Iron Maiden. That's the point of business analytics right here. That is the point of business analytics. Does that make sense, Jordan? Like, this is why we do what we do, is to create things like this so that someone can just easily input, or you can easily search through this. Like, you can just make results like that. So the point is not to, because if you want to use a code like this right here and you just want to make rules that have these conditions, you can write your function, you can algorithmically go through it, and now we've just made our own function right here, which makes really nice output. It kind of like separates the screen, and this is the kind of stuff I focus in on, like, how do you make things look nicer? So I have to know things like cat paste 0. Paste 0 just makes it so there's no spaces. If you do paste, it'll have spaces. By default, it'll do the sep with spaces, so it's going to look kind of crazy now. You're going to see like way too many spaces. It's just, you see all the extra spaces, so it adds a space every time there's this. Every time you do here, it adds a space. So if you do paste 0, what you see is what you get. There's no separation. So if you want the space by default, which you can change via the sep argument, you would just use paste. But if you want to like have exact output for what you want to see, you use paste 0, and paste 0 does no spaces. So this space right here is only created right down here because I created it there. So, but if I was using paste, I could just do this and it would put a space for me. But I want to control my spaces. Well, that's got it. That's got it for today. We got a lot of activities on Monday, but this is the goal of analytics, is to make easy to read, good output, have people utilize what we're doing, make functions, all that good stuff. We built a pretty cool function right here. So once again, you see the awesome function on the screen. Just practice. And I will see everybody on Monday. Jordan, great job. Keep up the great work. Bye, everybody. You know what? We're going to end with the outro today. We got to have a big outro. Here we go. Big outro for anyone still here. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.